When the universe cradles you in velvet silence, can the faint glow of ancient suns guide you to the mysteries hidden beyond sight? As the Milky Way's luminous river drifts past, what forgotten truths whisper from the spaces between its stars? And if every breath you take echoes the pulse of distant galaxies, how will you answer the invitation that beckons from the deepest void? In the immense darkness of space, a carpet of stars stretches endlessly in all directions, each pinprick of light a distant sun. Their glow is faint, yet persistent, a gentle reminder of life and energy scattered throughout the cosmos. As you float in this silent sea of light, the stars glitter softly around you, twinkling in the endless expanse. This serene starlight bathes your senses, comforting and beautiful in its constancy. In the gentle hush of this cosmic ocean, shadows also begin to emerge. Patches of deeper darkness drift between the bright points of light, a subtle contrast that makes the stars shine even more brightly. These are the peaceful shadows of space, regions as empty and silent as dreams, voids where nothing stirs. They are not threatening, but rather a quiet counterpoint to the stars. They feel like a vast, unfurled curtain behind the cosmic light, inviting a sense of calm and wonder. Far above you, the band of our own galaxy stretches across the sky like a gauzy veil, a silvery trail of countless stars. You drift through the spiral arms of the Milky Way, carried on a cosmic breeze. The great nebulae you see, those shimmering clouds of gas and dust, glow softly, as if lit by millions of tiny lanterns in the night. A sense of vastness settles over you again, as if you could reach out and touch the dust of stars born long ago. In the distance, even fainter lights wink. These are other galaxies, swirling cities of stars, their glimmer dulled by the eons of space between. They seem like ghostly beacons, far off and gentle. Each one holds its own universe of wonders, but here they are calm and distant, painting a serene backdrop. You feel gratitude for the quietude of this moment, knowing that these lights are patient. They will be here, unchanging, long after we are gone. Between these distant suns and worlds, you sense the primordial glow of background starlight and faint radiation. It whispers of the origins of time itself, a subtle hum from the dawn of cosmic history. It fills you with a gentle humility. You are a small part of a story that stretches back almost infinitely. And yet, you feel immense, part of the great fabric of the universe. The dichotomy of it all, being both infinitesimal and significant, is soothing rather than frightening. You remember how a single candle in a dark room can feel like a lighthouse in a storm. Here, each star is that candle. You find comfort knowing that the light around you is real and unwavering, even if it takes thousands or millions of years to reach this spot. Time itself feels soft. Events thousands of years ago are unfolding now in your vision. In this way, the past and present blend seamlessly, like a slow, comforting echo of eternity. In this boundless silence, your own breath is a gentle anchor. Each inhale is deliberate, a quiet reminder of life. With every slow exhale, you release any remaining tension. In the vast emptiness, each breath feels significant. There is no rush, no need to hurry. The universe itself seems to breathe along with you, a cosmic rhythm synchronizing with your calm. The silence is so complete, it feels velvety, as if the darkness itself is wrapping you in comfort. You let this velvet quiet envelop you, deepening your sense of peace. And yet, in this silence, you sense a subtle song of the cosmos. Not a sound you can hear, but a feeling, as if the stars themselves are humming a gentle tune. Perhaps it is the faint thrum of ancient particles, or the distant echo of an explosion that happened long ago. Whatever it is, it feels like a soothing melody woven into the fabric of space. It reassures you that in this vast emptiness, there is harmony. Far in the distance, tiny flickers of light pulse and fade. A distant pulsar blinks like a heartbeat in the darkness. A quasar glows softly and then dims. These flashes are muted now, like whispers on a breeze. They do not startle. They blend into the background of stars, adding their own quiet rhythm. You realize that even the most powerful cosmic phenomena have moments of rest when viewed from here. Each flicker is a small part of the larger harmony you are experiencing. The stars themselves seem to form subtle shapes in your vision. Constellations drift and shift, as if slowly dancing across the sky. You sense stories behind those patterns, tales of heroes and creatures from ages past. But here, those stories are told in feelings rather than words, a sense of wonder, a trace of awe. Watching these drifting patterns, you feel that you are part of an ancient narrative, listening to a story written in light and dark. You notice that the starlight around you carries faint, delicate colours. Hints of blue and orange appear in the brightest stars, like flares of twilight in the void. These colours swirl softly as you move, painting an aurora of starlight against the dark canvas. They are almost too subtle to see at first, but if you look patiently, they emerge like gentle brushstrokes of a cosmic painting. Even as you appreciate these wonders, you remain aware of your place in space. You are weightless, completely untethered to any world, drifting freely. There is no force pulling you, except this gentle invitation onward. You feel strangely at home here. There is no fear, only a profound curiosity. You realize that every light and shadow around you is an invitation to explore, and your mind quiets as you accept it. As you drift slowly onward, you notice a particularly deep and still shadow forming ahead. It grows wider and more profound as you approach, like the calmest part of night drawing near. Though it appears as an absence of light, there is something strangely alive in it, as if it holds a secret or a possibility. You feel an almost magnetic pull toward this darkness, a gentle curiosity awakening inside you. It is as if the darkness is saying, "Come closer. There is something hidden here waiting to be found." The starlight around you seems to change as you draw nearer to the shadow. Instead of glittering, the stars begin to stretch and smear across your vision, painting soft streaks of colour and warmth. The light around you bends and curves, as if the space itself is being gently pulled. Everything is serene, as if time has slowed to a languid pace. You can feel your own heartbeat, slow and steady, matching the calm rhythm of the universe. In this delicate dance of light and darkness, every star seems to whisper secrets of distant worlds, encouraging you to go deeper. At the center of that quiet darkness, a mysterious presence stirs. You cannot see it yet, but you sense its vastness. The blackness ahead is not merely empty. It feels deep and endless, as if it stretches beyond the limits of the cosmos. It does not frighten you. Instead, it intrigues you, filling you with a soft excitement and wonder. Perhaps this is the threshold of something extraordinary, a place where the familiar rules of the universe shift and change. You take one more gentle breath and let yourself drift forward, drawn by the quiet promise of what lies ahead. Gradually, a gentle sensation begins to stir within you. Something unseen, yet undeniable, reaches out with cosmic fingers. You realize that you are experiencing gravity's quiet power, the subtle tug of an invisible presence. It is not forceful or sudden, but steady and unceasing, guiding you onward. With each passing moment, the pull becomes more certain, not urgent, but insistent, like a warm invitation you cannot refuse. This recognition fills you with a calm determination. You understand that you are being carried onward, as if by gentle currents flowing through the void. The space around you shifts and curves almost imperceptibly, as if viewed through a pane of warped glass. Light from distant stars bends in soft arches, painting graceful streaks across the sky. The stars nearby seem to drift in smooth, serene orbits, as if tied to hidden spokes on a wheel of time. Watching this quiet ballet of celestial bodies, a deep sense of respect and awe washes over you. Gravity holds everything in place, weaving a delicate harmony among the wandering lights. You feel your body respond to this pull, even though you remain weightless. A subtle stretching sensation tugs gently at your limbs, as if the very fabric of space is bending around you. Time itself seems to slow in this region. Each moment stretches into the next in a long, peaceful flow. Your mind feels as expansive as the universe around you, and the quiet hum of gravity feels like a distant melody in your heart. It reassures you that even in this vast emptiness, there is connection and unity. Around you, the cosmic dance continues without haste. Nebula clouds twist slowly, like drifting mist. Star clusters glide in measured patterns, all guided by gravity's invisible hand. You watch as a single star, far ahead, bends its path slightly, curving gracefully around an unseen center, like a dancer following an invisible partner. Nearby, a ring of gas glows softly, its particles locked in a calm orbit. Even the photons of light here seem to pause for a heartbeat, curving around unseen contours as they journey past. It is as if the universe itself has paused in admiration of its own masterpiece. In this serene gravitational ballet, you feel a profound connection to the cosmos. Gravity, though invisible, feels almost personal now, like a warm embrace from the universe itself. It whispers that the smallest atoms and the grandest galaxies are bound by the same gentle laws. As you yield to this unseen force, you feel a deep trust and surrender. You have stepped beyond understanding gravity intellectually. You now feel it at your core. Its quiet guidance welcomes you deeper into the unknown, and you go forward without fear. Continuing onward, you approach the void, and now the darkness is framed by light. A great ring of glowing matter has formed at the edge of the emptiness. It is the accretion disk, a vast, soft-edged halo of gas and dust spiraling slowly, luminous in the blackness. Its light is gentle yet intense, like embers on the edge of a bonfire. The colours swirl with reds and oranges and deep blues, as if the night itself has been painted with the heat of distant suns. This ring warms your gaze without heat. It feels like looking at a familiar fire on a winter's night, but in an utterly alien landscape. Stars that wander too close have fallen into these orbits, their material becoming part of the disk. Even now, you see hints of stories in the light. Perhaps long ago a star ventured too near and was stretched into a stream of glowing gas, adding to this gentle blaze. From your perspective, this destructive event is serene, a cosmic transformation that released bright beauty. The process is slow and graceful, invisible in a moment, but you sense the scale of time here. What might seem cataclysmic is now just a smooth ribbon of light in your vision. Around the disk, you notice more delicate phenomena. Directly at the edge, there appears a faint, glowing circle, the photon ring, where light itself orbits the darkness one or more times before escaping. To you, it looks like a whisper of light drawn in a perfect loop around the void. Only the smallest flicker of it can be seen, but it hints at the incredible depths within. It feels like the boundary between worlds. On one side, our familiar universe. On the other, the unknown that lies beyond. You are at this threshold, and the universe seems to pause in its spinning to let you take it all in. As you linger, you also see other stars far beyond. They appear duplicated and smeared by gravity's trickery. A star behind the void may shine above and below it, or in rings of light around it, thanks to gravitational lensing. These ghostly images of stars create subtle halos, as if the cosmos itself is mirroring the sky. You feel delighted by these patterns, a sign that even amidst such a powerful force, light finds gentle ways to linger. Gravity distorts, but in this moment, it also creates its own art. Now, even time seems to behave differently. If you had a clock, you would see its hands moving more and more slowly as you approach. The closer you get to the edge, the slower the flow of time feels from your perspective. 1 second seems to stretch into many. It is not frightening. Instead, it feels like the universe giving you more time, a gift of extended presence, as if to savor the final view before the unknown. You notice a star on the brink of this darkness, orbiting slowly around the edge. Its light flickers gently, drawn out by the slow dance. It moves as if underwater, its motion beautifully elongated. You imagine that to the star, everything around it is slowed. The pulses of its own light would find hours in between beats. Yet from your vantage, it glows calmly, a last beacon at the threshold. You send out a silent greeting to that distant sun, as it too must feel both far away and intimately present. The silence here is profound. Any sound of cosmic winds or collisions has faded away. Only the gentle glow of light and the tug of gravity remain. You focus on how the scene makes you feel. Small, but safe and peaceful. There is no chaos, only a majestic calm. You understand that this is the threshold of the abyss, the very edge where the known universe fades. You take in the view with reverence, knowing that crossing this threshold will bring you into a realm unlike any other. But for now, you simply stand at the edge, breathing in the quiet and wonder. In this moment, you feel a sense of completeness. You have seen light and shadow, felt gravity and wonder. The stars have guided you to this edge. The largest mysteries of the universe are right before you, yet you are unafraid. You realize that even as you stand at the threshold, the universe holds you gently. You have arrived at the brink of the cosmic abyss, and now, softly and calmly, you pause, ready for whatever comes next. In the immense darkness of space, a carpet of stars stretches endlessly in all directions, each pinprick of light a distant sun. Their glow is faint, yet persistent, a gentle reminder of life and energy scattered throughout the cosmos. As you float in this silent sea of light, the stars glitter softly around you, twinkling in the endless expanse. This serene starlight bathes your senses, comforting and beautiful in its constancy. In the gentle hush of this cosmic ocean, shadows also begin to emerge. Patches of deeper darkness drift between the bright points of light, a subtle contrast that makes the stars shine even more brightly. These are the peaceful shadows of space, regions as empty and silent as dreams, voids where nothing stirs. They are not threatening, but rather a quiet counterpoint to the stars. They feel like a vast, unfurled curtain behind the cosmic light, inviting a sense of calm and wonder. Far above you, the band of our own galaxy stretches across the sky like a gauzy veil, a silvery trail of countless stars. You drift through the spiral arms of the Milky Way, carried on a cosmic breeze. The great nebulae you see, those shimmering clouds of gas and dust, glow softly, as if lit by millions of tiny lanterns in the night. A sense of vastness settles over you again, as if you could reach out and touch the dust of stars born long ago. In the distance, even fainter lights wink. These are other galaxies, swirling cities of stars, their glimmer dulled by the eons of space between. They seem like ghostly beacons, far off and gentle. Each one holds its own universe of wonders, but here they are calm and distant, painting a serene backdrop. You feel gratitude for the quietude of this moment, knowing that these lights are patient. They will be here, unchanging, long after we are gone. Between these distant suns and worlds, you sense the primordial glow of background starlight and faint radiation. It whispers of the origins of time itself, a subtle hum from the dawn of cosmic history. It fills you with a gentle humility. You are a small part of a story that stretches back almost infinitely. And yet, you feel immense, part of the great fabric of the universe. The dichotomy of it all, being both infinitesimal and significant, is soothing rather than frightening. You remember how a single candle in a dark room can feel like a lighthouse in a storm. Here, each star is that candle. You find comfort knowing that the light around you is real and unwavering, even if it takes thousands or millions of years to reach this spot. Time itself feels soft. Events thousands of years ago are unfolding now in your vision. In this way, the past and present blend seamlessly, like a slow, comforting echo of eternity. In this boundless silence, your own breath is a gentle anchor. Each inhale is deliberate, a quiet reminder of life. With every slow exhale, you release any remaining tension. In the vast emptiness, Each breath feels significant. There is no rush, no need to hurry. The universe itself seems to breathe along with you, a cosmic rhythm synchronizing with your calm. The silence is so complete, it feels velvety, as if the darkness itself is wrapping you in comfort. You let this velvet quiet envelop you, deepening your sense of peace. And yet, in this silence, you sense a subtle song of the cosmos. Not a sound you can hear, but a feeling, as if the stars themselves are humming a gentle tune. Perhaps it is the faint thrum of ancient particles, or the distant echo of an explosion that happened long ago. Whatever it is, it feels like a soothing melody woven into the fabric of space. It reassures you that in this vast emptiness, there is harmony. Far in the distance, tiny flickers of light pulse and fade. A distant pulsar blinks like a heartbeat in the darkness. A quasar glows softly and then dims. These flashes are muted now, like whispers on a breeze. They do not startle. They blend into the background of stars, adding their own quiet rhythm. You realize that even the most powerful cosmic phenomena have moments of rest when viewed from here. Each flicker is a small part of the larger harmony you are experiencing. The stars themselves seem to form subtle shapes in your vision. Constellations drift and shift, as if slowly dancing across the sky. You sense stories behind those patterns, tales of heroes and creatures from ages past. But here, those stories are told in feelings rather than words, a sense of wonder, a trace of awe. Watching these drifting patterns, you feel that you are part of an ancient narrative, listening to a story written in light and dark. You notice that the starlight around you carries faint, delicate colours. Hints of blue and orange appear in the brightest stars, like flares of twilight in the void. These colours swirl softly as you move, painting an aurora of starlight against the dark canvas. They are almost too subtle to see at first, but if you look patiently, they emerge like gentle brushstrokes of a cosmic painting. Even as you appreciate these wonders, you remain aware of your place in space. You are weightless, completely untethered to any world, drifting freely. There is no force pulling you, except this gentle invitation onward. You feel strangely at home here. There is no fear, only a profound curiosity. You realize that every light and shadow around you is an invitation to explore, and your mind quiets as you accept it. As you drift slowly onward, you notice a particularly deep and still shadow forming ahead. It grows wider and more profound as you approach, like the calmest part of night drawing near. Though it appears as an absence of light, there is something strangely alive in it, as if it holds a secret or a possibility. You feel an almost magnetic pull toward this darkness, a gentle curiosity awakening inside you. It is as if the darkness is saying, "Come closer. There is something hidden here waiting to be found." The starlight around you seems to change as you draw nearer to the shadow. Instead of glittering, the stars begin to stretch and smear across your vision, painting soft streaks of colour and warmth. The light around you bends and curves, as if the space itself is being gently pulled. Everything is serene, as if time has slowed to a languid pace. You can feel your own heartbeat, slow and steady, matching the calm rhythm of the universe. In this delicate dance of light and darkness, every star seems to whisper secrets of distant worlds, encouraging you to go deeper. At the center of that quiet darkness, a mysterious presence stirs. You cannot see it yet, but you sense its vastness. The blackness ahead is not merely empty. It feels deep and endless, as if it stretches beyond the limits of the cosmos. It does not frighten you. Instead, it intrigues you, filling you with a soft excitement and wonder. Perhaps this is the threshold of something extraordinary, a place where the familiar rules of the universe shift and change. You take one more gentle breath and let yourself drift forward, drawn by the quiet promise of what lies ahead. Gradually, a gentle sensation begins to stir within you. Something unseen, yet undeniable, reaches out with cosmic fingers. You realize that you are experiencing gravity's quiet power, the subtle tug of an invisible presence. It is not forceful or sudden, but steady and unceasing, guiding you onward. With each passing moment, the pull becomes more certain, not urgent, but insistent, like a warm invitation you cannot refuse. This recognition fills you with a calm determination. You understand that you are being carried onward, as if by gentle currents flowing through the void. The space around you shifts and curves almost imperceptibly, as if viewed through a pane of warped glass. Light from distant stars bends in soft arches, painting graceful streaks across the sky. The stars nearby seem to drift in smooth, serene orbits, as if tied to hidden spokes on a wheel of time. Watching this quiet ballet of celestial bodies, a deep sense of respect and awe washes over you. Gravity holds everything in place, weaving a delicate harmony among the wandering lights. You feel your body respond to this pull, even though you remain weightless. A subtle stretching sensation tugs gently at your limbs, as if the very fabric of space is bending around you. Time itself seems to slow in this region. Each moment stretches into the next in a long, peaceful flow. Your mind feels as expansive as the universe around you, and the quiet hum of gravity feels like a distant melody in your heart. It reassures you that even in this vast emptiness, there is connection and unity. Around you, the cosmic dance continues without haste. Nebula clouds twist slowly, like drifting mist. Star clusters glide in measured patterns, all guided by gravity's invisible hand. You watch as a single star, far ahead, bends its path slightly, curving gracefully around an unseen center, like a dancer following an invisible partner. Nearby, a ring of gas glows softly, its particles locked in a calm orbit. Even the photons of light here seem to pause for a heartbeat, curving around unseen contours as they journey past. It is as if the universe itself has paused in admiration of its own masterpiece. In this serene gravitational ballet, you feel a profound connection to the cosmos. Gravity, though invisible, feels almost personal now, like a warm embrace from the universe itself. It whispers that the smallest atoms and the grandest galaxies are bound by the same gentle laws. As you yield to this unseen force, you feel a deep trust and surrender. You have stepped beyond understanding gravity intellectually. You now feel it at your core. Its quiet guidance welcomes you deeper into the unknown, and you go forward without fear. Continuing onward, you approach the void, and now the darkness is framed by light. A great ring of glowing matter has formed at the edge of the emptiness. It is the accretion disk, a vast, soft-edged halo of gas and dust spiraling slowly, luminous in the blackness. Its light is gentle, yet intense, like embers on the edge of a bonfire. The colours swirl with reds and oranges and deep blues, as if the night itself has been painted with the heat of distant suns. This ring warms your gaze without heat. It feels like looking at a familiar fire on a winter's night, but in an utterly alien landscape. Stars that wander too close have fallen into these orbits, their material becoming part of the disk. Even now, you see hints of stories in the light. Perhaps long ago a star ventured too near and was stretched into a stream of glowing gas, adding to this gentle blaze. From your perspective, this destructive event is serene, a cosmic transformation that released bright beauty. The process is slow and graceful, invisible in a moment, but you sense the scale of time here. What might seem cataclysmic is now just a smooth ribbon of light in your vision. Around the disk, you notice more delicate phenomena. Directly at the edge, there appears a faint, glowing circle, the photon ring, where light itself orbits the darkness one or more times before escaping. To you, it looks like a whisper of light drawn in a perfect loop around the void. Only the smallest flicker of it can be seen, but it hints at the incredible depths within. It feels like the boundary between worlds. On one side, our familiar universe. On the other, the unknown that lies beyond. You are at this threshold, and the universe seems to pause in its spinning to let you take it all in. As you linger, you also see other stars far beyond. They appear duplicated and smeared by gravity's trickery. A star behind the void may shine above and below it, or in rings of light around it, thanks to gravitational lensing. These ghostly images of stars create subtle halos, as if the cosmos itself is mirroring the sky. You feel delighted by these patterns, a sign that even amidst such a powerful force, light finds gentle ways to linger. Gravity distorts, but in this moment, it also creates its own art. Now, even time seems to behave differently. If you had a clock, you would see its hands moving more and more slowly as you approach. The closer you get to the edge, the slower the flow of time feels from your perspective. 1 second seems to stretch into many. It is not frightening. Instead, it feels like the universe giving you more time, a gift of extended presence, as if to savor the final view before the unknown. You notice a star on the brink of this darkness, orbiting slowly around the edge. Its light flickers gently, drawn out by the slow dance. It moves as if underwater, its motion beautifully elongated. You imagine that to the star, everything around it is slowed. The pulses of its own light would find hours in between beats. Yet from your vantage, it glows calmly, a last beacon at the threshold. You send out a silent greeting to that distant sun, as it too must feel both far away and intimately present. The silence here is profound. Any sound of cosmic winds or collisions has faded away. Only the gentle glow of light and the tug of gravity remain. You focus on how the scene makes you feel, small, but safe and peaceful. There is no chaos, only a majestic calm. You understand that this is the threshold of the abyss, the very edge where the known universe fades. You take in the view with reverence, knowing that crossing this threshold will bring you into a realm unlike any other. But for now, you simply stand at the edge, breathing in the quiet and wonder. In this moment, you feel a sense of completeness. You have seen light and shadow, felt gravity and wonder. The stars have guided you to this edge. The largest mysteries of the universe are right before you, yet you are unafraid. You realize that even as you stand at the threshold, the universe holds you gently. You have arrived at the brink of the cosmic abyss, and now, softly and calmly, you pause, ready for whatever comes next. In the depths of our galaxy, we venture inward. The starlight grows denser as we approach a crowded central bulge of ancient suns. Invisible clouds of interstellar dust cloak our view in visible light. Yet beyond this veil lies a profound darkness. There, at the Milky Way's secret heart, an immense presence makes itself known, not through light, but through its gravitational pull. Stars whirl in frenetic orbits around an unseen center, like fireflies caught in a silent, cosmic dance. Something enormous is hiding in the shadows. The beating heart of our galaxy, Sagittarius A, a supermassive black hole. This central giant, Sagittarius A, resides some 26,000 light-years from Earth, right in the core of the Milky Way. By mass, it is about 4 million times heavier than our Sun. Yet despite its titanic mass, it emits no light of its own. Instead, it lurks as a dark pit in spacetime, a sleeping giant, nourished only by trickles of infalling gas and dust. Over years of patient observation, astronomers discerned its presence through the motion of stars. One star in particular, known as S2, loops around the void with astonishing speed. It completes one ellipse in just 16 years, rushing to within about 18 billion kilometers of the hidden mass, roughly 4 times Neptune's orbit, a hair's breadth in galactic terms. At its closest approach, S2 hurtles at nearly 3% the speed of light, flung by an invisible hand. Such a tight, rapid orbit could only be caused by an object of incredible mass packed into a tiny volume. It was the smoking gun that revealed Sagittarius A as a black hole, the central supermassive black hole of the Milky Way. Gliding closer in our mind's eye, we picture the scene. Surrounding the black hole is a swarm of stars, the S-cluster, a dense handful of suns moving like a swarm of bees near a hive. These stars live out their lives under the gravitational thrall of Sagittarius A, their paths bent and their speeds accelerated by its gravitation. The environment here is extreme. Space itself is curved steeply around the black hole. If we could see in radio or infrared, we would witness a faint glow from hot gas spiraling toward the dark center. This glow marks the last photons escaping just outside the event horizon, the point of no return. Inside that boundary, no light or signal can ever escape to space. For decades, Sagittarius A was a mere hypothesis, a radio source with a mysterious asterisk. It was first detected in 1974 as a compact radio emission amid the broader haze of the galactic core. Early on, it earned the moniker Sagittarius A star for its curious, energetic nature. But only at the turn of the 21st century did technology allow us to trace the orbits of individual stars there, clinching the case that an immense compact mass lurked at the center. In 2020, 2 astronomers, Reinhard Genzel and Andrea Ghez, were awarded the Nobel Prize in Physics for their decades of observations that proved our galaxy's heart harbors a supermassive black hole. Their teams watched stars like S2 swing around an unseen object, using infrared telescopes to peer through the dust and capture these stellar motions. The calculations were inexorable. About 4 million solar masses confined in a space no larger than our solar system. No known cluster of objects could be so massive and yet invisible. Only a black hole fit the bill. Even so, for years, Sagittarius A remained an unseen phantom. Then, in May 2022, a breakthrough. Astronomers unveiled the first ever image of the gentle shadow of Sagittarius, using the Event Horizon telescope. This image was not a photograph in visible light, but a radio image synthesized from observatories across the globe, effectively creating an Earth-sized dish peering at our galactic center. It revealed a faint halo of emission, a fuzzy donut of light surrounding a dark central region. That dark center is the silhouette of the black hole itself, about 50 microarcseconds across on the sky, equivalent to a mere 51.8 million kilometers in diameter. To put that in perspective, the span of this shadowy maw is smaller than Mercury's orbit around the Sun. It's a mind-bending thought. All the mass of 4 million suns crushed into a void with a diameter only about 1/3 the width of Earth's orbit. Seeing this image, a blurry ring of light in Sagittarius, was humanity's first direct glimpse of our own galaxy's central black hole. It provided incontrovertible evidence that this dark object is indeed what theory predicted, a black hole beyond any reasonable doubt. Despite its presence at the dynamic center of the Milky Way, Sagittarius A, today is remarkably quiescent. It's often described as a quiet or wimpy black hole on a meager diet. Unlike the voracious central black holes in some galaxies, our own is comparatively docile. It consumes only small amounts of material, a diet perhaps equivalent to a human eating 1 grain of rice every million years. In astronomical terms, it's practically fasting. Because of this, the environment around Sagittarius A is relatively subdued. The gas around it glows faintly, but not in the overwhelming blaze seen in more active galactic nuclei. Astronomers suspect magnetic fields and limited fuel keep it underfed, preventing major outbursts. It means that, for now, our black hole slumbers in a state of supermassive serenity. Yet serenity does not mean total stillness. Occasionally, Sagittarius A stirs and flashes to remind us it is still active on some level. Over the years, telescopes have caught unexplained flickers and flares from our galactic center. One dramatic episode occurred in 2019. The area just outside the black hole's event horizon suddenly brightened twice as much as ever seen before. For a brief moment, Sagittarius A flared, emitting a surge of infrared light as gas was rapidly heated near the brink of oblivion. We have never seen anything like this in the 24 years we have studied the supermassive black hole, one astronomer remarked. The normally demure object suddenly flared with unprecedented intensity, hinting that a chunk of matter had just been swallowed in a sudden gulp. The flare soon subsided, and the black hole returned to its quiet state. But such events show that even a sleeping dragon can twitch in its slumber. Scientists eagerly investigate these flares, as they are windows into the black hole's behavior. What causes a normally quiet black hole to suddenly burp with light? One possibility was the close pass of a star named S02 in 2018. As S02 swooped near, perhaps it dragged a stream of gas that only a year later finally swirled down into the black hole, igniting a burst of energy. Another tantalizing possibility involves a bizarre object named G2. In 2014, astronomers watched a mysterious cloud of gas and dust called G2 approach Sagittarius A. Many predicted a spectacular display of tidal disruption, the cosmic giant tearing the cloud to shreds and lighting up as it devoured the debris. But to everyone's surprise, G2's encounter was anticlimactic. The cloud wasn't torn apart as expected, and the anticipated fireworks largely fizzled. Some later argued G2 might have been not a pure gas cloud at all, but a star with a cocoon of gas that held it together. In any case, Sagittarius A barely stirred during that encounter, displaying only mild flares. This resilience earned it a reputation as a quiet monster, one that can absorb a stray passing cloud with hardly a peep. Only years later did we catch the black hole in an unusually feisty moment, those 2019 flares. Perhaps G2's remnants or other clumps of material finally made their inward plunge, triggering Sagittarius A's brightest known outburst. In 2018, another significant flare was observed. Sagittarius A became about 75 times brighter in X-rays than usual, then faded. Astronomers suspect it might have swallowed an asteroid or comet-sized object, a one-time snack that caused a sudden flash. These episodes are rare thrills in what is otherwise a placid environment. Most days, Sagittarius A is content to flicker and simmer with low-level activity. Small X-ray and infrared flares occur daily or weekly as tiny clumps of matter fall in and briefly heat up. After each flicker, the black hole returns to its gentle state. It's a bit like watching the coals of a dying fire. Occasionally a spark flies, hinting at the tremendous power quietly biding its time. Now, imagine we could approach even closer, though in reality, no spacecraft could survive such a journey. Drawing near the event horizon of Sagittarius A, the view would be unlike anything we know. Starlight from behind the black hole would bend and smear into rings of light due to gravitational lensing. Time itself would slow dramatically from an outside perspective. If we sent a probe, its signals would stretch and redshift, struggling to escape the severe gravity. For the probe, on the brink of the event horizon, the rest of the universe would seem to speed up, while from our vantage it would appear frozen, fading as its light loses energy. This is the strange physics that plays out around a black hole, even a calm one like Sagittarius A. Just beyond the invisible boundary, space and time themselves are twisted in the grip of 4 million suns crushed into a point. Although we cannot see beyond that horizon, we know its size. Sagittarius A's event horizon radius is on the order of 17 solar radii, about 12 million kilometers, and the shadow captured in the radio image corresponds to roughly 51 million kilometers across, when including gravitational light bending. The Milky Way's central black hole is small compared to the solar system. If you placed it where our Sun is, its event horizon would fit well within Mercury's orbit. All of our solar system's planets could orbit outside the black hole's edge with room to spare. The idea that such a relatively small region can contain millions of solar masses defies common sense. Yet the evidence is there. Sagittarius A is an extreme warp in spacetime, a pinprick of unbelievable density. And yet, for all its might, it's quiet. It's not currently devouring large stars or gas clouds in a frenzy. Our black hole is like a great whale drifting slowly through dark waters, mouth open but swallowing only the tiniest of plankton. The surrounding ring of gas and dust feeds it so sparsely that it emits only a feeble glow. If we were to look for Sagittarius A with an optical telescope, we'd see nothing. Visible light is blocked by intervening dust. And even if it weren't, the black hole emits little in that spectrum. We rely on infrared and X-ray eyes to catch its subtle moods. Over millions of years, there have likely been times when our galactic center was more turbulent. Astronomers find evidence in X-ray echoes and gamma-ray bubbles that Sagittarius A had episodes of higher activity in the past. Giant gamma-ray structures called the Fermi bubbles, billowing above and below the Milky Way's plane, might be ancient blowouts from our black hole, tens of thousands of years ago, when it ingested a big meal and burped out energy. Even today, using sensitive detectors, scientists catch hints of these past feasts. faint X-ray flares reflected off distant gas clouds, arriving decades or centuries later, which suggests that centuries ago Sagittarius A was brighter for a time. It seems our sleeping giant is not permanently dormant. It dozes, occasionally stirring, and perhaps in the future could awaken again if a fresh supply of fuel falls in. For now, we regard Sagittarius A with a mix of awe and relief. Awe, because it's a monster in our midst, a black hole of staggering mass right in the core of our home galaxy. Relief, because it slumbers gently, posing no threat to us at 26,000 light-years remove. The Sun and our solar system orbit this distant dark mass roughly once every 250 million years, completely unaware of the cosmic predator at the center. Only sophisticated instruments and careful measurements betrayed its presence. To us, living our lives under the sun's warm glow, the Milky Way's black hole is a silent guardian at most, anchoring our galaxy with its gravity, but affecting our daily existence not at all. Our journey now widens its scope. We have met the singular heart of the Milky Way and felt its quiet pull. But Sagittarius A is not unique. In fact, the more we look, the more we realize that nearly every large galaxy in the universe carries a similar heavy heart. The Milky Way's central black hole is one of countless supermassive black holes scattered throughout the cosmos. Some are smaller, many are far larger. They lurk in the cores of galaxies, spiral and elliptical, big and small. These are the giants at galactic hearts, each one a gravitational titan shaping its host galaxy in ways subtle and profound. As we drift outward from our galactic center and begin to explore others, we encounter a dizzying variety of black hole leviathans. In the great Andromeda galaxy, our nearest large neighbor, a central black hole of about 100 million solar masses, lies quietly among a crowded star hub. In giant ellipticals like M87, a galaxy visible in Virgo, the central black hole swells to billions of solar masses. Indeed, the very first black hole ever imaged was the one in M87, back in 2019, by the same Event Horizon telescope that later turned to Sagittarius A. M87's monster weighs an estimated 6.5 billion suns, and its shadow was seen as a sharp glowing ring, an iconic image of a supermassive black hole's event horizon silhouette. That tremendous black hole powers a jet of energy piercing out of the galaxy's core, which we can photograph in visible light as a faint bluish streak shooting tens of thousands of light years into space. The sheer range of scales is astonishing. Sagittarius A, at millions of solar masses, is actually on the small side for central black holes. We have now discovered ultramassive black holes that tip the scales at tens of billions of solar masses. One of the heaviest known, the quasar TON 618, boasts an almost inconceivable mass around 66 billion suns. If Sagittarius A is a king, such ultramassive black holes are emperors among giants. They likely sit at the centers of the largest galaxies in the universe, often galaxies that are the product of many mergers and eons of accretion. One recent discovery, using gravitational lensing, found a 33 billion solar mass black hole in a galaxy some 2.7 billion light-years away. These ultramassive beasts push the limits of what our theories can explain, and they occupy the highest rungs of black hole magnitude. Yet, for all their enormity, supermassive black holes often live quiet lives, much like Sagittarius A. Only under certain conditions do they reveal themselves dramatically. Typically, when a supply of gas or stars is readily available, for instance during a galaxy merger, or in a young galaxy rich with primordial gas. the central black hole can become active and light up brilliantly. Otherwise, it can remain a dark, lurking influence. In cosmic surveys, we find that most mature galaxies today host dormant black holes. They sit in gravitational dominion, but unseen until provoked. Almost every galaxy hides at least one such supermassive black hole at its core, as a kind of central anchor. These black holes and their galaxies likely grew up together. As galaxies formed and evolved over billions of years, their central black holes also gained mass, through accreting gas, consuming star clusters, or merging with other black holes when galaxies collided. There seems to be a profound link between a black hole and its host galaxy. Remarkably, the mass of a galaxy's central black hole often correlates with the mass of the galaxy's central bulge of stars. This hints that the formation of stars and the growth of the black hole were connected, perhaps through feedback loops of energy and matter. Consider what happens when galaxies collide, as they often do in the grand ballet of the universe. When two galaxies merge, their once separate cores, each harboring a supermassive black hole, will eventually sink toward the center of the new merged galaxy. For a time, a pair of black holes may orbit one another, a duet of darkness spiraling closer in a gravitational dance. Slowly, inexorably, they draw together. In the final moments, they merge into one, releasing an enormous pulse of energy, not in light, but in gravitational waves, ripples through the fabric of space-time itself. If we could hear the universe, this would be a deep, resonant chirp, signaling the birth of an even mightier black hole. These events, the mergers of supermassive black holes, happen in deep cosmic time, and their gravitational echoes wash over the cosmos. Modern astronomers are now detecting a background hum of low-frequency gravitational waves, which may well be the combined chorus of countless supermassive black hole pairs slowly spiraling across the universe. When such a merger happens, the newly enlarged black hole may be jostled or sent ringing with vibrations, but eventually it settles into a quiescent state, unless a lot of gas is funneled to it during the galaxy merger, in which case a luminous flare or extended active phase might occur. In many cases, galactic mergers can ignite a dormant black hole, giving birth to a bright active nucleus, or even a quasar, which we will soon encounter during the tumultuous union. After the fireworks, as the new galaxy stabilizes, the central black hole might again become quiet, having cleared out or heated much of the surrounding fuel. The influence of a supermassive black hole on its galaxy can be subtle yet significant. Through a process termed feedback, an active black hole can regulate star formation in its host. When the black hole devours matter rapidly, it can expel tremendous energy, powerful radiation and winds, even jets of plasma moving at near light speed. These outflows can heat up or sweep away the gas in the galaxy's core, the very gas that would otherwise cool and condense into new stars. In essence, a periodically active black hole can govern the growth of its galaxy, preventing it from making new stars for a time, and thus shaping the galaxy's size and appearance. Our Milky Way's black hole likely had such outbursts long ago that helped carve out the center of our galaxy, and the evidence may remain in the large cavities and shock fronts we detect in high-energy emissions around the galactic center. Conversely, under some circumstances, black hole outflows might compress gas in certain regions, triggering bursts of star formation in a halo or neighboring galaxy. The relationship is complex, a kind of feedback loop between the galaxy and its central giant, often characterized as the galaxy's central engine, giving both life and limitation to its surroundings. When the fuel is spent or blown away, the galaxy's center grows calm again, and the black hole enters a serene phase, as ours has. Thus, we have cycles, periods of ferocious activity and light, alternating with long stretches of quiet darkness. Supermassive serenity is the default state we observe in galaxies like our Milky Way. Peering across space, we see many galaxies with modest, elderly cores, their central black holes largely idle. Only a faint glimmer in radio or X-ray betrays the presence of the gravitational titan. It's a peaceful existence, a sleeping giant quietly binding the galaxy together. The stars in the galaxies bulge, orbit under its gravitational influence, but they're mostly unaffected by any radiation or outflows, since the black hole isn't roused. For perhaps millions of years, the giant will remain in this quiescent condition, until fate or chance sends new fuel its way. One can't help but sense a cosmic balance in these life cycles. Too much activity from the black hole and the galaxy's star formation is quenched. Too little, and gas can accumulate again. In this way, the black hole and its host seem to co-evolve, each influencing the other's growth. This delicate interplay plays out over eons, maintaining a kind of equilibrium. Our own black hole's serenity has allowed the Milky Way to continue forming stars at a slow rate, and likely enabled life to arise in the galactic suburbs undisturbed. Had Sagittarius A been a rampaging quasar at this moment, the radiation, even at our distance, could potentially have impacted the development of complex life on Earth. But here we are, in a galaxy with a temperate heart. Now, to truly appreciate the might and influence of these cosmic giants, we turn our attention to those special times when they do awaken in full fury. If supermassive black holes are typically sleeping giants, then quasars are their awakened form, giants in a feeding frenzy. When a black hole accretes matter at a high rate, the infalling gas doesn't plunge straight in. It forms a swirling accretion disk orbiting the black hole, like water circling a drain. The friction and gravitational shear within this disk heat the gas to extraordinary temperatures, millions of degrees, causing it to blaze with light. This disk can shine across the electromagnetic spectrum. Visible light, ultraviolet, X-rays, even gamma rays, all pouring out from a region not much larger than our solar system. Additionally, magnetic fields can channel some of the energetic material into twin jets that shoot outward along the black hole's rotational poles. These jets, narrow and incredibly powerful, can extend for tens or hundreds of thousands of light years, drilling through the galaxy and beyond, broadcasting the black hole's presence like a cosmic beacon. The result of all this is one of the most luminous phenomena in the universe, a quasar. The term quasar is short for quasi-stellar radio source, a historical name from the 1960s when astronomers first encountered these objects as faint, star-like points emitting strong radio waves. They appeared quasi-stellar, looking like stars in telescopes, yet their spectra and energy output were unlike anything seen before. It was eventually realized that these stars were not stars at all, but the brilliant cores of distant galaxies, powered by accreting supermassive black holes. The reason they looked star-like is that their galaxies were so distant, and often faint, that only the bright nucleus was visible. The surrounding galaxy's light was drowned out by the nucleus's glare. Observing a quasar in a distant galaxy is like seeing only a car's headlight in the dark of night. The headlight's brightness overwhelms any sight of the car itself. When we see a quasar, we are witnessing a black hole in its active glory, a beacon shining from the depths of space. Quasars are typically found in the distant universe, which also means we are looking back in time at the universe's youth. In fact, The farther we look, the more common quasars become, telling us that billions of years ago, black holes were more frequently active, likely because there was more fuel available in those early epochs. Many quasars we observe are from 10 to 12 billion years ago, a time when galaxies were young and often rich in gas or undergoing mergers, providing ample meals for their central black holes. To get a sense of just how radiant a quasar can be, consider this. Quasars can emit energy hundreds of times greater than an entire galaxy of stars. A single quasar's luminosity can be up to 1,000 times brighter than the Milky Way. All the billions of stars in our galaxy, shining together, would be outshone by a factor of 1,000 by one quasar in a remote galaxy. It's almost unfathomable. For example, the first quasar ever identified, 3C273 in the constellation of Virgo, is about 2.5 billion light-years away. That immense distance is hard to imagine, and yet 3C273 is so bright that with a moderate-sized telescope, it can be seen from Earth as a tiny point of light. If we could somehow bring 3C273 much closer, say just 30 light-years from Earth, it would outshine every star in the night sky. In fact, it would be as bright as our sun in the sky. That gives an inkling of its power. At 2.5 billion light-years away, it still can be detected. Move it to the neighborhood of the sun, and it would be blinding. Astronomers have determined that 3C273's luminosity is on the order of a few trillion times that of our sun, or several hundred times the luminosity of the entire Milky Way. The quasar pours out thousands of times the energy of all the stars in a galaxy. Such brilliance defies easy comprehension. It is the energy of gravity, liberated as matter descends into a bottomless well. What does the engine of a quasar look like up close? We envision an orbiting disk of gas, so hot that it glows white-blue, threaded by intense magnetic field lines. As the black hole spins, and most are thought to spin rapidly, it drags space around it, twisting those magnetic fields into a tight helix. Part of the inflowing matter, instead of falling straight in, gets funneled by this magnetism into two outgoing streams. These relativistic jets erupt from the north and south poles of the black hole, often appearing as narrow beams of plasma that shoot out well beyond the host galaxy. Inside the jets, particles are accelerated to speeds near light, producing strong radio waves and often X-rays and gamma rays as well. If we were to hover at a safe distance, we might see a brilliant quasar core with twin jets like beacons above and below it, extending outward and gradually dissipating into intergalactic space. The light from the accretion disk, meanwhile, is not steady. It can flicker and change, sometimes dramatically. Quasars have been observed to vary in brightness over timescales of days or months, indicating that the emitting region, the disk, is only light days or light weeks across, since a larger region couldn't vary so quickly in unison. This is astonishing. Something the size of our solar system, or smaller, is outshining 100 billion stars. All that energy originates from a relatively tiny volume. It's the ultimate power plant, fueled by gravity and fed by matter. According to physics, accretion onto a black hole is a very efficient way to convert mass into energy, more efficient than nuclear fusion in stars. When matter falls in, about 10% of its mass energy can be released as light and kinetic energy. For comparison, fusion in the sun converts only 0.7% of mass to energy. This is why even a small amount of mass, if rapidly accreted, can produce prodigious luminosity. Historically, quasars were a big mystery. When 3C273 was identified in 1963, the realization of its distance due to its high redshift and brightness shocked astronomers. Here was an object as small as a star by appearance, yet capable of emitting more light than galaxies. Over the 1960s and 1970s, about 100 quasars were found, all very distant, leading to speculation about what they were. By the 1980s, the active galactic nucleus, AGN, model, a supermassive black hole with an accretion disk, became accepted as the explanation. Today, we know quasars are one variety of AGN, the most extreme on the spectrum of brightness, typically when the black hole is both massive and accreting at a high rate. Less active black holes produce Seyfert galaxies or radio galaxies, similar principle but not as blazingly bright, allowing us to see the host galaxy too. In Seyfert galaxies, for instance, the nucleus is bright, but not enough to completely overwhelm the galaxy's starlight. Quasars, in contrast, are the cases where the black hole is such a dominant light source that from afar it outshines everything else. Quasars truly are beacons in the dark. They serve as cosmic lighthouses that allow us to probe the distant universe. Because they are so luminous, we can observe quasars from incredibly far away, even when they originate from a time when the universe was very young. The most distant quasars known are seen as they were less than 1 billion years after the Big Bang. For example, one quasar named J0313 1806 has a redshift indicating we see it just 670 million years post-Big Bang. Yet it harbours a black hole over 1 billion solar masses. The existence of such a massive black hole so early in cosmic history challenges our understanding. How could it grow so big, so fast? These distant beacons are forcing astronomers to refine theories of black hole formation and growth. Perhaps they started as massive seed black holes born from direct collapse of gas, or from the mergers of many smaller black holes in dense protogalaxies. However it happened, the early universe was aflame with quasars, and each quasar illuminates not just its host galaxy, but the intergalactic medium around it. We see, in the spectra of quasars, imprints of primordial gas, fingerprints of the raw hydrogen and helium, laced with the first heavy elements from early stars, lying along our line of sight. Quasar light thus acts like a flashlight shining through the fog of the early cosmos, revealing the content and distribution of matter across billions of light years. As we gaze at a quasar's light, we are in a sense reading the diary of the universe's adolescence. The quasars tell us that by that era, supermassive black holes were already in place, some with masses of 1 billion suns or more. They tell us that galaxies were forming and that these black holes were feasting. And through careful study, we find that quasar activity tends to peak at certain epochs, roughly around 10 billion years ago, a few billion years after the Big Bang. After that peak period, the number of quasars diminishes towards the present day, indicating that galaxies exhausted their surplus gas or settled into calmer configurations. Today, in the nearby universe, quasars are rare. The ones that do exist are often associated with recent galaxy interactions or other unusual circumstances that have provided new fuel to a central black hole. One famous nearby example is not a quasar per se, but an active nucleus, the radio galaxy Centaurus A, where a relatively massive black hole, 55 million solar masses, accretes matter from a disrupted smaller galaxy, generating spectacular jets and radio lobes. It shows on a smaller scale what a more subdued quasar might look like when the galaxy is not extremely distant. But true quasars, as originally defined, are mostly far-flung objects from a younger universe. Let's picture a specific quasar to bring it to life. Take 3C273 again, since it's historically important and one of the closer quasars. If we zoom in with Hubble Space Telescope and other advanced telescopes, we can actually discern some structure. We block out the blinding central point with a coronagraph, a device to hide the brightest light, and suddenly we see a dim host galaxy around it. It turns out 3C273 resides in a giant elliptical galaxy. We also see a remarkable jet of plasma emanating from the core, visible even in optical light, extending some 200,000 light-years, evidence of the black hole's powerful engine launching material outward. This jet shows up as a faint, smoky filament in images, and its existence was one of the first clues that quasars are connected with energetic outflows. For 3C273, measurements indicate the jet is moving at relativistic speeds, and it emits across radio and optical wavelengths as it collides with intergalactic medium. This kind of jet is a common feature in many quasars, especially those that are strong radio sources, hence the original term radio source. Some quasars, viewed from certain angles, we call blazars, where one of the jets is pointed almost directly at Earth, making them appear even brighter and more variable due to relativistic effects. Even after decades of study, quasars maintain an aura of mystery simply because of the extremes involved. The idea of something as small as a solar system outshining a galaxy, or a black hole gobbling matter and turning it into jets that affect intergalactic space, is exotic and mesmerizing. And yet quasars have been pivotal in advancing our understanding of the cosmos. They provided crucial evidence that the universe evolves. In the steady state versus Big Bang debates of mid-20th century, the discovery that quasars were more common in the past and essentially non-existent nearby strongly supported the idea of a changing universe, not a steady state one. Quasars also helped cement the notion that black holes are real and can reach colossal sizes when this was still theoretical. And they have become tools for probing everything from dark matter to the cosmic web by serving as bright background lights for absorption studies. Now, as our imaginary journey takes us through the epoch of quasars, we find ourselves bathed in their light, witnessing the universe at its most energetic. But we also know that this phase is transient. Given enough time, even the brightest quasar will exhaust its immediate fuel. The accretion disk will wane, the jets will fade, and the quasar will dim to a memory, leaving a quiet, massive black hole once more at the galaxy's center. That galaxy, perhaps having merged or evolved, might settle into a long, stable existence, with the black hole simply part of its infrastructure, occasionally feasting on a star or gas cloud, but mostly inconspicuous. Our Milky Way might have gone through a quasar-like state in its youth, perhaps not as bright as a 3C273, but certainly more active than today. If an outside observer in a distant galaxy were to look at the Milky Way 10 billion years ago, they might have seen a modest quasar or Seyfert nucleus. Now, they'd see a normal galaxy with no standout active nucleus, unless they had sensitive instruments to pick up the weak radio and X-ray emission from Sagittarius A. It's humbling to realize that galaxies can wear different faces across cosmic time. Fiery quasar in youth, placid majesty in middle age. In the grand tapestry of the cosmos, quasars mark the chapters where galaxies and black holes grow up. They are the beacons illuminating the deep dark, helping structure the universe by blowing bubbles in the primordial gas, seeding turbulence, and perhaps influencing where subsequent generations of galaxies could form. Each quasar we observe is a lighthouse whose beam has travelled billions of years to reach us. When that light left the quasar, our own sun and earth did not yet exist. Now, as it arrives, we decode its messages and marvel at the power that emitted it so long ago. Drifting away from the quasar epoch, we return to the present universe. Around us, the vast darkness between galaxies is quieter now. The quasars have mostly dimmed. Only a few continue to shine here and there. We live in an era dominated by mature galaxies, many with quiescent cores. But the story of black holes isn't over. Far from it. We have seen what they are and what they can do. From the silent guardians, like Sagittarius A, to the brilliant quasars, lighting up the young universe. Each black hole holds secrets behind its event horizon, mysteries we have yet to unravel. What lies in that endless night beyond the horizon? What happens deep in the belly of these gravity giants, where the known laws of physics strain and perhaps break? As our journey continues, we will step even further into the unknown, into the very shadow of the cosmic abyss, where the normal world ends and something else begins. The next leg of our expedition will carry us into those ultimate mysteries, as we venture in the shadow of black holes, ever deeper into the cosmic abyss, where space and time themselves twist and fate of matter and information come into question, and where our understanding of reality faces its greatest test. Black holes have long been seen as the silent giants of the cosmos. These enigmatic voids devour everything that strays too close, even light itself, and in their grip, all forms of signal seem to vanish. For a time, it seemed nothing that happened around a black hole could ever be witnessed directly by distant observers. And yet, despite their darkness and silence, black holes are not entirely mute. When they stir in just the right way, they cause the very fabric of space and time to tremble. In those subtle tremors, ripples moving invisibly across the universe, black holes announce their presence. These are gravitational waves, the faint echoes of the abyss. In essence, a gravitational wave is a ripple in the cosmic fabric itself. When massive objects accelerate or collide, they disturb space-time and send out waves, much like a stone dropped into a still pond sends ripples across the water. But unlike water waves that we can see or hear, these ripples in space-time are incredibly subtle. They stretch and squeeze the distance between objects ever so slightly as they pass, and then they fade into the void. Over a century ago, Albert Einstein's new theory of general relativity first hinted at the existence of such waves. His equations showed that even if two massive bodies were locked in orbit, unseen, say, two black holes circling in the dark, they would stir the fabric of space-time itself, launching faint vibrations that travel outward at the speed of light. Einstein himself doubted we would ever be able to detect these waves, believing that by the time they reached Earth, they would be vanishingly small. For decades, gravitational waves remained a theoretical idea, a beautiful prediction of relativity with only indirect hints of their reality. Scientists could only infer their presence, for example, by observing a pair of neutron stars slowly spiraling closer together at exactly the rate Einstein's theory predicted if gravitational waves were carrying away their orbital energy. These confirmations always came indirectly, never revealing the waves themselves. Black holes especially seemed destined to keep their collisions secret, hidden in darkness. It took decades of patient work, but scientists were determined to catch these cosmic whispers. They built enormous, extraordinarily sensitive observatories on Earth. In effect, giant ears listening for space-time to quiver. The most ambitious of these is the Laser Interferometer Gravitational Wave Observatory, better known as LIGO. In two remote locations, one in Washington State and another in Louisiana, LIGO uses long tunnels with suspended mirrors and laser beams to measure tiny changes in distance. If a gravitational wave passes through Earth, it will stretch space in one direction and squeeze it in the perpendicular direction by a minute amount. LIGO was designed to detect a change in length as small as 1/10,000th the width of an atom's nucleus, an astonishing level of precision. With such instruments finally in place and tuned, humanity was ready at last to hear the universe's faintest vibrations. And then, in the early morning hours of September 14th, 2015, the silence was broken. A faint, unmistakable ripple was recorded in LIGO's detectors. It was incredibly subtle, a brief chirp in the data that lasted barely 0.2 of a second, but it was real. For the first time, we had directly detected a gravitational wave. Scientists soon realized what they had caught: the final signal from a cataclysmic collision of two black holes in a distant galaxy. This event was immense beyond imagining. Analysis of the wave revealed that it originated about 1.3 billion light-years away, from two black holes, each roughly 30 times the mass of our Sun, spiraling into each other. In their last moments, those black holes were orbiting dozens of times per second, approaching half the speed of light, before finally colliding. The impact was so powerful that about 3 suns' worth of mass was converted into pure energy in an instant. That energy shot out in the form of gravitational waves. At the peak of the merger, the power of the emitted gravitational waves was staggering, on the order of 50 times greater than the light power of all the stars in the observable universe combined. Yet by the time those waves traversed 1 billion light-years to reach Earth, they were incredibly faint. The fabric of space here stretched and squeezed by only a tiny fraction of an atom's width. It was as if the universe shouted, but the distance was so great that by the time the call arrived, it was just a whisper. Even so, LIGO's exquisitely tuned ears picked it up. In that fleeting chirp, we heard the echo of two black holes merging in the cosmic abyss. This discovery marked the dawn of a new era in astronomy. A century after Einstein's prediction, gravitational waves were no longer theoretical. They were observed, unmistakably, opening a new window onto the cosmos. Black holes, once thought to be completely undetectable when colliding, had announced themselves through the fabric of spacetime. The achievement confirmed that Einstein's general relativity still held true under the most extreme conditions, and it showed that we humans could indeed tune in to the universe's most elusive signals. The world of science rejoiced. The pioneers of this effort, the scientists and engineers who built LIGO and made the detection possible, were soon recognized with the highest honors, including the 2017 Nobel Prize in Physics. But beyond the accolades, there was a deep, collective sense of wonder. We had not only seen the shadow of black holes, now we could hear their voices, faint but profound, echoing across time and space. The first gravitational wave detection was only the beginning. Almost immediately after that breakthrough, scientists kept their detectors listening, eager to catch more cosmic events. And the universe did not disappoint. Before long, additional faint ripples began arriving from the depths of space, each one the signature of another colossal merger. It turned out that such cosmic collisions, once purely theoretical, are happening all around the universe, and now we could finally sense them. With our newfound ability to hear gravity, a hidden population of black hole collisions started coming to light. Dozens of gravitational wave signals have been recorded since 2015, most of them from black holes merging in distant galaxies. Each detection is like a story unfolding. Two invisible giants spiraling together, ending in a sudden, violent union. Picture one of these distant collisions. For millions of years, two black holes orbit in a lonely dance, gradually drawing closer as they radiate away energy in gravitational waves. As they approach, their orbital speed increases from 1 orbit per day to 1 per hour, to 1 per second, until, in the final moments, they are whipping around each other at nearly the speed of light. In that instant, the two collapse into one, releasing a burst of gravitational energy. Space-time rings with the brief, powerful vibration of their merger, and then falls quiet again. Many of the black hole pairs we've detected are similar in scale to the first event. Black holes a few dozen times the sun's mass merging. But some have pushed the boundaries of what we imagined. In one spectacular case, scientists observed a merger between two unusually massive black holes, one roughly 85 times the mass of the sun and the other about 66 times. When these titans crashed together, they formed a single black hole of approximately 142 solar masses. It was the first clear confirmation of an intermediate mass black hole, a breed larger than those born from individual stars, yet far smaller than the supermassive black holes in galaxy cores. Such a monster had never been detected before. Its birth via merger proved that black holes can grow by consuming each other, step by step, building up mass in a cosmic hierarchy. The gravitational waves from that event carried the imprint of this historic formation, allowing astronomers to revel in a discovery that had eluded them for decades. Not all gravitational wave tales are solely about black holes, either. In the growing catalogue of cosmic collisions, there have been events involving other dense objects. In 2020, the instruments caught an especially intriguing signal: a black hole swallowing a neutron star. This was the first time such a mixed merger had been witnessed. Neutron stars are the ultra-dense remnants of massive stars, essentially stellar cores compressed to the density of an atomic nucleus. One can imagine the scene: a neutron star, itself a ball of tightly packed neutrons left over from a supernova, ventures too close to a black hole. The black hole's gravity stretches the neutron star into a teardrop shape, tearing it apart, or in some cases swallowing it whole, in one final act of violence. As the neutron star is consumed, the disturbance in space-time sends out a mournful gravitational wave signal, like a final cry of the devoured star. LIGO and Virgo heard this cry, adding yet another chapter to the cosmic collision story. Proof that black holes can merge not just with each other, but with other exotic objects as well. And then there are collisions that involve no black holes at all: neutron-star pairs. In August 2017, gravitational wave detectors picked up the inspiraling death dance of two neutron stars merging. We will soon discuss this event in detail, but it's worth noting here because it was a tremendous milestone. Unlike black hole mergers, which are dark events, two neutron stars colliding create an explosion of light and matter in addition to gravitational waves. For the first time, astronomers were able to both hear the gravitational waves of a collision and see the brilliant flash of its aftermath with telescopes. This dual observation confirmed theories about the origin of mysterious gamma-ray bursts, and even revealed that such stellar smash-ups forge heavy elements like gold in their fiery debris. The neutron-star merger was a shining example of how gravitational waves have opened a new kind of multisensory astronomy, one that engages not just our sense of sight, but the newfound sense of cosmic hearing. Each collision we detect enriches our understanding of the cosmos. These events tell us how often black holes meet and merge, and under what conditions. Already, the abundance of detections implies that the universe is teeming with far more black holes than we could infer from light alone. In years past, astronomers would only suspect a black hole pair if they saw X-rays flickering from gas around them. Now we can find them by their gravitational whispers, even when they're otherwise invisible. The data from gravitational waves have revealed, for instance, that some black holes are spinning rapidly, while others have orbits oddly tilted relative to their spins. clues to how they formed and later encountered each other. We've learned that black hole collisions can occur in distant young galaxies and ancient star clusters alike, wherever massive stars have lived and died. It's as if an entirely hidden ecosystem of black holes has suddenly been illuminated, one merger at a time. What's more, these observations are still only in their infancy. As our detectors become more sensitive, we expect to hear even fainter or more distant collisions. During observing runs in recent years, new gravitational wave events have been detected on a regular basis, sometimes several in a single month, as the instruments quietly listen to the sky. With planned upgrades and additional detectors joining the network, the concert of cosmic collisions will become even richer and clearer. We may even detect the gravitational waves from truly gigantic mergers. Imagine the slow, powerful reverberation from two supermassive black holes, the kind at the centers of galaxies, as they spiral together after galaxies collide. Those waves are like deep bass notes, with wavelengths so long that ground-based detectors like LIGO cannot easily pick them up. But scientists are devising new ways to listen for these majestic events, from future space-based detectors to clever observations of pulsars acting as cosmic metronomes. The era of gravitational wave astronomy has only just begun, and each new improvement in our listening instruments promises to unveil phenomena we've never heard before. For now, the collisions we can detect have already transformed our view of the universe. A picture is emerging of a dynamic, restless cosmos, where massive objects continually merge and reshape themselves. Black holes that were once invisible in the darkness are now being mapped through their subtle tremors. Every ripple we catch is a messenger from a previously hidden realm, carrying information about the most extreme places and events. And yet, with all we have gleaned so far, we sense that there is much more to come. Signals out there still too faint or too low-pitched for us to detect, from events even more grand. The cosmic symphony is far from over. We are only now tuning in to hear its full range, preparing to listen ever more deeply to the songs of the universe. The cosmos is no longer silent to us. We have gained not just a new tool, but a new sense, an ability to listen to the universe. And what we've heard so far is already reshaping our understanding. Yet, we are still in the early days of this grand auditory exploration. Day by day, our gravitational wave observatories continue to scan the skies, ears pressed against the fabric of spacetime for the slightest tremble. As they do, the scope of what we can detect is growing. Our two LIGO detectors in the United States have been joined by Virgo in Europe and Kagra in Japan, forming a global network of gravitational wave listening posts. Together, they improve our sensitivity and let us pinpoint where in the sky a signal comes from by comparing the timing at multiple sites. New detectors are planned, including one in India, which will further enhance this worldwide hearing array. With each upgrade, the cosmic whispers become a little clearer, the distance we can probe a little farther. We are also extending our reach by moving beyond Earth. One of the most ambitious endeavors on the horizon is to place gravitational wave detectors in space. Without the noise and interference of our planet, a space-based observatory can listen for the deep, slow waves that ground-based instruments miss. The Laser Interferometer Space Antenna, or LISA, is a mission under development that will send 3 spacecraft to orbit the Sun in a huge triangle formation, millions of kilometers apart. Using lasers to measure tiny fluctuations in their separation, LISA will be tuned to hear low-frequency gravitational waves, the kind produced by truly colossal events like merging supermassive black holes. When it launches in the 2030s, LISA is expected to open another new window on the universe, capturing the gravitational rumble of cosmic giants and perhaps signals from exotic phenomena we have only dreamed of. It's almost as if we're about to add a new range of notes to our cosmic symphony, bringing in the deep bass that our current detectors cannot register. Meanwhile, in a very different way, astronomers have already begun listening for those low bass notes, using the galaxy itself as an observatory. They have turned to pulsars, rapidly spinning neutron stars that emit beams of radio waves, as tools to detect the slowest gravitational waves. Pulsars are like precise clocks scattered across the Milky Way. Each time their radio beam sweeps past Earth, we detect a pulse. By carefully timing these pulses from many pulsars, scientists can notice tiny irregularities, slight delays or advances in the ticks of these cosmic clocks that are correlated across the sky. Such correlations indicate that spacetime between us and the pulsars is being gently stretched and squeezed by giant gravitational waves passing through. After years of observations, multiple teams of astronomers announced in 2023 that they have found evidence for a persistent gravitational wave background permeating the universe. This background is like a deep cosmic hum, a low-frequency chorus, likely caused by countless pairs of supermassive black holes slowly spiraling over eons. The precise rhythmic dance of the pulsars has revealed this subtle music. In essence, we've discovered that the universe has a gravitational heartbeat, a steady rumble from the combined murmurs of ancient black hole binaries. It's a bit like standing in a rainforest and hearing the distant chorus of countless insects and animals. No single source stands out, but together they create a persistent background song. This discovery of the gravitational wave background is a remarkable confirmation that the universe is indeed filled with gravitational waves on all scales. It also hints at phenomena we have yet to directly witness, like the actual merger of supermassive black holes. The background hum we detected suggests that somewhere, many somewheres, enormous black holes are orbiting each other right now, destined to collide in the far future. In the coming decades, with advanced pulsar timing and space detectors like LISA, we hope to isolate individual notes in that low-frequency symphony. Perhaps the final crash of two galaxy-core black holes coming together, an event that would make the detectors on Earth sing with a slow, powerful waveform lasting hours. To prepare for that, scientists around the world are honing both their instruments and their analytical techniques, making sure we're ready to catch these profound events when they occur. Equally transformative is how gravitational wave listening has begun to work in tandem with traditional astronomy. The neutron star merger we mentioned earlier, the one in 2017, was a watershed moment for this multi-messenger approach. When LIGO and Virgo sensed the gentle rise and fall of gravitational waves from two neutron stars spiraling together, they alerted astronomers worldwide. Within seconds, a gamma-ray burst was detected by orbiting telescopes, and within hours, dozens of observatories swung to the patch of sky triangulated by the gravitational wave detectors in a galaxy. They found a new point of light, the afterglow of the neutron star's collision, shining in every wavelength from radio to X-rays. It was the first time we both heard and saw the same cosmic event. This single event confirmed decades-old theories. It proved that at least some gamma-ray bursts are caused by neutron star crashes, and it demonstrated that such collisions are the cosmic forges of precious metals like gold and platinum. Scientists were elated. It was as if we had suddenly gained the ability to both see lightning and hear thunder from a distant storm, having previously been deaf to the thunderclap. The combination of information from gravitational waves and electromagnetic waves painted a far richer picture than either could alone. Now, multi-messenger astronomy has become a cornerstone of cosmic exploration. When gravitational wave detectors pick up a signal, rapid alerts go out so that telescopes can quickly scan the corresponding region of sky for any flashes or new stars. Conversely, when astronomers observe something unusual in light, say an unexpected burst of high-energy radiation, they check if any gravitational wave chirp coincided with it. The synergy between listening and looking is giving us a fuller sensory experience of cosmic events. It feels as though the universe, long observed in silence, is now being experienced in a rich audio-visual symphony. We witness the fireworks of phenomena and simultaneously feel the subtle tremors they send through spacetime. Each mode of observation enhances the other. Gravitational waves carry information about things light cannot directly show, like the mass and motion inside a merger, and electromagnetic observations reveal aspects that gravitational waves can't, like the chemistry of exploding debris. Together, they provide a holistic narrative of cosmic events, from the invisible build-up to the visible aftermath. As we continue to refine our gravitational hearing, what might the future hold? We could detect waves from the earliest moments of the universe, primordial gravitational waves imprinted on the cosmos when it was less than a second old. These would be relics of the Big Bang, or its immediate aftermath, carrying clues about how space and time behaved at incomprehensibly high energies. Efforts are underway to find these traces, whether through subtle patterns in the cosmic microwave background or ultra-sensitive detectors in space. If we succeed, we would be, in effect, listening to the echo of creation, a sound from the dawn of time. Even in the realm of black holes, unanswered questions beckon us forward. Gravitational waves have confirmed their existence and allowed us to measure their mergers, but mysteries linger. For instance, according to quantum theory, black holes might not be eternal. Stephen Hawking proposed that they very slowly evaporate by emitting faint thermal radiation. No one has ever observed this Hawking radiation. But if black holes do evaporate, what becomes of everything that fell inside? There's an ongoing puzzle about whether information that enters a black hole is lost forever or somehow preserved, the so-called black hole information paradox. These deep questions lie at the intersection of gravity, quantum physics, and thermodynamics, and they remind us that there is much about the cosmic abyss we still don't understand. Thus, our journey into the shadow of black holes continues, propelled by both new observations and new ideas. With gravitational waves, we have started to illuminate the darkness, hearing the otherwise inaudible signals of merging black holes and neutron stars. With multi-messenger astronomy, we have begun to piece together a fuller story of cosmic cataclysms. And with theoretical breakthroughs yet to come, we hope to unravel what happens in the most secret heart of a black hole. We stand on the threshold of profound discoveries, listening to the cosmos with a sense of wonder. The more we learn, the more the mystery deepens, and the more the quiet void of space seems to come alive with the music of the spheres. In the next leg of our journey, we delve even deeper into those mysteries, seeking answers to questions that challenge the limits of our knowledge, and venturing further into the shadowy frontier of the cosmic abyss. In the silence beyond a black hole's edge, we step into the unknown. Time and space twist in ways we cannot fully grasp. We cross the threshold of the event horizon, beyond which nothing can ever come back. Light, sound, even matter, fade into darkness. The gentle glow of distant stars drifts away, and we imagine ourselves adrift in a place where our understanding of physics loses its way. The cosmos has hidden its deepest secrets behind this invisible boundary. For an intrepid traveler crossing this boundary, the journey inward is an ordeal of surreal distortions. Gravity intensifies, stretching bodies and bending light into great strands. Every direction pulls toward the center, as if space itself funnels all paths inward. The ticking of time itself may change, flowing more slowly or losing its familiar meaning. We whisper calmly about what might happen, though no one can truly know what awaits beyond the horizon. As we drift further in, theory predicts we might approach a singularity, a point where the mass of the black hole condenses to infinite density. Space and time become infinitely curved, and our equations unravel. This is the quiet heart of mystery, hidden forever behind the event horizon. Even as gravity crushes all we know into a single point, there is no light or sound there, only silence. We realize that here, physics as we know it fades, leaving us with questions that have no answers yet. Even as we contemplate the darkness inside, we gain no information from the outside. Hawking radiation, a faint quantum glow at the edge, might carry hints of secrets, but any clues are feeble and lost in cosmic noise. Some physicists have proposed that the black hole's surface, its event horizon, could somehow encode the memory of everything it has consumed, like a vast cosmic hologram. Yet none of these ideas can pierce the veil completely. All we know is that the ultimate fate of anything that crosses this threshold remains locked away forever, hidden behind layers of darkness we cannot penetrate. Imagine a traveler daring to fall into the abyss. To them, the journey might at first seem uneventful, but soon the immense gravity would begin to stretch and pull on every part of their body. Inch by inch, they would be elongated, as if they were strands of light drawn between opposing forces. Time around them would seem to stretch, running more slowly than for a distant observer. Yet they themselves would feel the moments passing normally, living each breath until the very end. This surreal strength of gravity highlights how differently we experience this crossing, marking the frontier of what we can know. In our minds, crossing the horizon is like sailing beyond the most distant shores of a cosmic sea. We plunge into waters so deep that no light returns, leaving us enveloped in darkness. The event horizon marks this boundary, where all light and hope fade. Beyond this boundary, reality is as strange to us as the depths of an uncharted ocean. Still, the gentle tug of wonder remains strong, tempting us to imagine what hidden depths might lie beneath the surface. As explorers of the universe, we rely on the faint signals surrounding a black hole to tell its story. We gaze at the fiery rings of gas and dust as they whirl into oblivion, heating and glowing brightly before vanishing forever. That brilliant dance is all we can observe, the final farewell of materials spiraling into darkness. Nothing from the abyss beyond the horizon ever reaches us. All the secrets of the interior remain inaccessible to any instrument we possess. Still, this edge, this shimmering veil of truth at the brink of nothingness, invites our curiosity. To learn about black holes, scientists also look for signals from violent events. When massive stars explode or black holes collide, they send out waves that ripple through the fabric of space-time. We detect these gravitational waves and watch glowing disks of matter feeding the black hole. But all of this is happening at the edge. These observations remain outside the horizon. They remind us how stubbornly the black hole guards its secrets. We can study only the light and gravity at its edge, not the abyss within. We linger at the threshold of knowledge, ears straining in cosmic silence, as the unknown waits quietly within. Though the black hole itself offers no answers, Its very existence sparks our imagination. We dare to imagine hidden passages or other phenomena that could hint at deeper truths. Perhaps there are cosmic tunnels that connect distant parts of the universe. With gentle hearts and curious minds, we turn our gaze beyond the black hole's dark door toward the next great mystery. Space, with its stars and galaxies, is like a vast ocean stretching in all directions. We often picture it as smooth and empty, but Einstein taught us that it can bend and stretch under the influence of mass and energy. Imagine the cosmos as a giant rubber sheet. If we fold that sheet so that two distant points touch, a bridge would appear. In that instant, those far apart points share a secret path. This is the wormhole idea, a direct passage through the sea of space, where the usual distance vanishes. Our curiosity carries us to another idea. What if there are hidden passages in the cosmos that connect distant realms? Imagine space itself as a kind of fabric. In our mind's eye, we fold this fabric until two far apart points touch each other. A wormhole, often imagined as a cosmic tunnel, would be like such a fold, a shortcut through the darkness. It is a splendid dream. If such a portal were traversable, one might travel instantly between faraway galaxies. But reality may be far more uncertain. In the early days of relativity, Einstein himself pondered such strange geometry. Along with colleague Nathan Rosen, he discovered a solution where two regions of spacetime could be linked by a bridge. These Einstein-Rosen bridges, or wormholes as they are now called, tantalize our imagination. But there is a catch. Classical theory predicts that these tunnels would pinch themselves closed almost instantly. It's as if the cosmic tunnel collapses the moment one steps inside. Perhaps this simple picture remains a beautiful thought experiment. Decades later, physicist Kip Thorne speculated on more optimistic conditions. He noted that if we could thread a wormhole with something called exotic matter, matter with negative energy, it might stay open. Such exotic matter would act like scaffolding, propping up the tunnel against gravity's pull. In that picture, a stable cosmic tunnel might be possible. But negative energy is unlike anything we encounter in everyday life. It remains only a theoretical idea, like a magic ingredient in a cosmic recipe. Science fiction has shown us wormholes as swirling portals in the sky. They light up our dreams, linking distant stars or even times. But on this journey of understanding, we must distinguish fancy from fact. So far, no wormhole has been found, and the physics suggests any real wormhole would be incredibly difficult to create, let alone navigate. Still, these cosmic dreams inspire scientists to look beyond the obvious, to wonder what hidden passages might exist. Curiously, quantum physics allows tiny fluctuations in space-time, a froth of miniature tunnels that appear and vanish in an instant. In this quantum foam, microscopic wormholes could briefly exist, but these would be far too small to travel through, and too short-lived to change anything for larger scales. Even if such fleeting tunnels exist at the smallest level, a stable, human-sized wormhole remains far beyond our reach. Astronomers have even tried to find traces of such tunnels. Some have searched the sky for strange gravitational lensing or patterns in the cosmic microwave background that might betray the presence of a wormhole. Others have listened for unusual gravitational signals. So far, their searches have returned silence. The universe has not revealed any clear sign of a cosmic shortcut. At least for now, wormholes remain as elusive as the daydreams we project onto the night sky. These cosmic tunnels capture our dreams of reaching beyond known boundaries. They suggest that the vast spaces between stars could somehow be bridged in an instant. Yet nature often surprises us. We have no evidence they actually exist, and our best theories doubt it. Still, wonder moves us forward, and sometimes dreams inspire discovery in unexpected ways. Remarkably, even here on Earth we see tiny glimpses of exotic phenomena. In the laboratory, the Casimir effect can create regions of slight negative energy between carefully placed plates. This suggests that in quantum physics, unusual energies can arise in miniature. Yet using this to prop open a wormhole would demand quantities of negative energy billions of times larger than anything we can produce. These laboratory hints are interesting, but fall far short of making an actual cosmic tunnel possible. Even if a wormhole could be formed and kept open, traversing it might be perilous. The moment we step through, we would enter regions of extreme curvature. Tidal forces could stretch us like strands, and time might shift in strange ways. The journey could feel like traveling through a storm, both wondrous and dangerous. In dreams we cross the void with a gentle breeze, but in reality we would face the fury of physics as we approach the unknown. And yet, we continue to dream. Even the search for wormholes teaches us something about our universe. It reminds us how vast and strange the cosmos is. It keeps our minds open to possibilities beyond the ordinary. Whether or not such tunnels truly exist, the idea alone expands our imagination. We continue to gaze at the stars with wonder, knowing that every great discovery once began with a dream. Another speculative ingredient in these cosmic ideas is the concept of cosmic strings. These are hypothetical strands of energy woven through the universe. Some physicists have wondered if a cosmic string, looping through a wormhole, could help prop it open. It's an elegant idea, a celestial rope holding open a tunnel in space. But cosmic strings remain hypothetical too. We've never found one. This reminds us that each step toward exotic science is a step into the unknown. If we do ever find a wormhole, even a small one, it would revolutionize space travel and physics. Imagine stepping through a gateway in space to reach a star on the other side of the galaxy within a moment. It would make interstellar journeys as easy as bending light. We would have to rewrite the rulebook of space exploration. The search alone pushes our technology and understanding to new heights. For now, wormholes remain a dream of the future, guiding scientists onward. One curious property of wormholes, at least in theory, is their link to time itself. In the math, if one end of a wormhole were moved, it could allow backward travel in time, a wild idea that leads to strange paradoxes, like meeting your younger self. Yet such time-bending journeys remain purely speculative. Many physicists suspect that nature would prevent these paradoxes from arising, perhaps by making wormholes unstable or forbidding them altogether. It reminds us that even our boldest dreams must bow to the subtle rules of the universe. Some of the most advanced ideas in physics hint at exotic possibilities. In string theory, extra dimensions might hide natural tunnels through spacetime. In brain-world scenarios, our universe could be like a sheet floating in a higher dimensional space, and wormholes might stretch into the unseen bulk. These visions are mathematically beautiful, but completely untested by experiment. They lie beyond our reach for now. For the moment, they serve as inspiration, like maps of unseen continents drawn by mathematicians. Dreams of cosmic travel are more than idle fantasies. They reflect a deep drive to explore. Just as early sailors imagined lands beyond the horizon, We now dream of reaching distant stars. Every mention of a wormhole or shortcut is a tribute to that human curiosity. These ideas push us to build better telescopes, devise new mathematics, and probe the universe more deeply. In a way, wormholes are like ships of hope, carrying our questions across the vast unknown. Now, as we set aside the swirling realm of cosmic daydreams, we return to the quiet promise of truth at the black hole's core. There, beyond all tunnels and illusions, lies the singularity, the most profound mystery of all. With our minds calm and our hearts steady, we prepare to venture into that silent heart of mystery once again. According to Einstein's theory, the very center of a black hole is a singularity, a place where density becomes infinite and our laws break down. But infinite is just a signal that our equations have lost meaning. It's like driving smoothly on a road, only to face a giant wall with no clue what lies beyond. The mathematics gives up at that point. There is no formula for what happens at infinite density. It stands as the quiet heart of mystery at the center of darkness. The singularity is not a room or a cave. It is where space and time themselves collapse. All paths through a black hole lead inevitably to that one point. Imagine space being pulled tighter and tighter, like stretching dough until it becomes a single, infinitely dense knot. At the singularity, there is no inside or outside in the normal sense, only this one inexorable point. Distance and volume disappear, leaving a single pure point of infinite gravity. Because nothing can escape from inside, the singularity is utterly silent. No light comes out, no sound travels. Even the gravitational waves we detect come only from outside events. It's as if this point sits in the deepest quiet of the cosmos. It hears nothing and echoes nothing. We call it a heart, but it beats with silence. Anything that falls in seems to vanish into this silent center. The singularity cares only about total mass, spin, and charge. It knows nothing of the details left behind. It's as if every object is frozen in time and space, buried under the weight of gravity. The details of what has fallen are lost to us, subsumed into the whole. Our only clues about what lies within come from how the outside world is influenced by the black hole's mass and rotation. Physicists believe that at a singularity, we must merge our understanding of the very large with the very small. Perhaps space might become grainy at these extremes, and matter could behave in unfamiliar ways. Some theories suggest that instead of an actual infinite point, the core could be smoothed out by quantum effects. In that picture, a black hole might have a tiny, almost indiscernible core instead of a true singularity. But right now, these remain just ideas, because we have no working theory that unites relativity and quantum mechanics. Some scientists wonder if nature might avoid a true infinite point at all. They suggest that when a black hole collapses, it could end in an ultra-dense state called a Planck star. This would be extremely tiny, a point of extreme but finite density held apart by quantum pressure. If that is true, then the singularity as we think of it never truly exists. Instead, there is a hard limit to how far gravity can compress. It's a bold idea that remains to be proven. Over unimaginably long eons, Hawking radiation will cause even a black hole to shrink and vanish. In that final stage, we wonder, what happens to the singularity? Does it somehow fade away or release its hidden content? We honestly do not know. The fact that a black hole can evaporate suggests the singularity might not be eternal. Perhaps at the very end, some subtle imprint of its secrets leaks back into the universe. If so, the story of each black hole might end, not in absolute silence, but in a gentle whisper. In truth, singularities represent the frontier of our ignorance. Each black hole's center holds one, and each whispers of questions beyond our reach. To really study them, we would have to unite two pillars of modern physics: the cosmic rules of Einstein and the quantum laws of atoms, which we have not yet done. This puzzle humbles us. It reminds us that even with all our knowledge, we can't fully describe the quietest hearts of the cosmos. Yet hope remains that someday, with new ideas or data, we might unlock their secrets. For now, all we can do is listen from outside. We watch how black holes bend space and send ripples through the fabric of time. We detect gravitational waves when they merge, and glowing light from the matter that orbits them. But the singularity itself remains utterly silent. It neither signals nor surrenders any knowledge. It is, truly, the quietest mystery of all. If you were falling in toward that central point, you might reach it in a finite amount of your own time. From your perspective, the journey ends at that silent point, in a finite number of moments. For you, the singularity marks the final instant. But from the outside universe's view, it's unreachable. A faraway observer would never actually see you hit the singularity. You would appear to slow down and freeze at the edge. In one sense, the singularity is both very near and forever out of reach, like the horizon of an impossible journey. In fact, if the black hole is large enough, you might not feel anything violent the moment you cross the horizon. Nothing dramatic announces the crossing. The laws of physics remain smooth. It's only later, as you continue inward, that the pull intensifies beyond what any living thing could survive. This contrasts with small black holes, where the gravitational difference from your head to your feet would tear you apart long before you reach the center. In cosmic giants, weighing billions of suns, the fall into darkness could be much more gradual. Outside, a black hole can be a vibrant source of energy. Matter spiraling in heats up and may spit out powerful jets of particles and light. Yet this spectacle remains forever outside the event horizon. At the singularity, all that drama stops. The chaos of the accretion disk vanishes, replaced by silence. There is no explosion at the core, only the final endpoint of collapse. Even the gravitational waves we detect come from the outer dance of black holes. The singularity itself emits none. Its only message to us is carried through its mass, spin, and charge. We see a black hole's silhouette and know how strong its gravity is, but no whisper comes from within. The singularity itself has no hair, nothing recognizable we can see, for all other details are lost to us. If somehow we could cross the singularity's boundary, what would lie beyond? In classical relativity, there is no beyond. Space and time simply end. Some have imagined new universes or dimensions beyond that point, but those notions are wildly speculative and untestable. In truth, the notion of beyond a singularity is outside our current understanding. The singularity is not a gateway. It is the end of the road for our known spacetime. Some scientists believe in a sort of cosmic modesty, the idea that singularities should never be exposed. This cosmic censorship suggests we will never see a naked singularity laid bare to the universe. Instead, each one is shrouded by an event horizon. It's as if nature insists on covering its raw mathematical infinities behind a curtain of darkness. Under that veil, the singularity lies still, hidden from any prying eyes. A black hole is the ultimate black box of nature. We see only what goes in and what comes out, never seeing inside. The singularity is the far end of that box, forever hidden. As scientists, this reminds us of humility. We learn from the edges, but the deepest secrets might always hide beyond our senses. There is a strange beauty in that. Even as the singularity keeps its silence, it inspires us to keep searching, questioning, and learning. According to classical relativity, every black hole that exists must have a singularity at its core. It is as certain as the predictions of Einstein's equations. We have found nothing to contradict this, though all we see are external effects. If we ever detect something unexpected, it could overturn that certainty. For now, the singularity stands as the inevitable conclusion of collapse in our current understanding. Over the years, theorists have tried to imagine what could replace the singularity. One idea is the fuzzball of string theory, a tangle of vibrating strings instead of a point. Another is the gravastar, a shell of exotic matter instead of a singular center. These are attempts to avoid an actual mathematical infinity. But so far, all these models still hide behind an event horizon, keeping the interior sealed. None of these alternatives have experimental support yet. They remain imaginative possibilities on the cutting edge. Right now, our view of singularities is entirely theoretical. We infer their presence from equations and from how black holes behave externally. No probe can go there. No particle can escape to tell the tale. Our picture is sketched from mathematics and imagination, guided by the shadows left on the stage. Even so, the idea of a singularity teaches us something profound. It highlights the limitations of our current theories and stands as a signpost pointing toward new physics beyond our horizon. Ultimately, singularities remind us of our limits. They are mysterious and intimidating, but they also inspire awe and curiosity. They force us to admit what we do not know. In a way, the silence of a singularity is as eloquent as any revelation, a quiet hint that the universe still holds secrets we have not deciphered. It is a testament to the ever-continuing journey of discovery. And so we linger in the calm shadows cast by these mysteries. We have explored as much as imagination and science allow. Yet the heart of darkness still holds its secrets. We step away, not with answers, but with wonder in our hearts. Ahead lies another horizon to approach, another chapter waiting to unfold. Our journey continues onward, into the next part of our cosmic voyage. In an era far beyond our own, after the last suns have flickered and died, a deep darkness has settled across the cosmos. The galaxies that once shone brightly have receded into unimaginable distance and vanished from sight. If we could stand at that future horizon and look up, we would see a sky bereft of familiar lights. No glowing band of the Milky Way, no nearby galaxies, not even a faint star. The universe's grand lights have one by one been snuffed out. No new stars are born anymore. The cosmic fuel for creation is exhausted. All that remains are faint embers of what was, cold, dim remnants of long-dead suns, and black holes, lurking as silent sentinels in the endless night. For a time, scientists debated how the universe might meet its end. Would it conclude in fire or in ice? Some imagined a fiery collapse, a big crunch, where gravity would one day halt the expansion and pull everything back into a final implosion, perhaps to spark a new Big Bang and rebirth the cosmos. In that vision, the universe could be cyclic, an eternal phoenix rising from its own ashes time and again. But the universe had other plans. In the late 20th century, astronomers discovered that the expansion of the universe is not slowing down at all. In fact, it is speeding up, driven by a mysterious force they call dark energy. Rather than contracting toward a hot rebirth, space itself is stretching ever more rapidly. All signs now point toward an end, not with a bang, but with an ever colder, ever quieter whimper. As the eons pass, galaxies drift further and further apart in the growing emptiness. Just a couple trillion years from now, an eye blink compared to the eternity that follows, other galaxies will have slipped beyond our horizon of visibility, carried away by the accelerating expansion of space. Their light, stretched to oblivion, will no longer reach us. The universe will become a lonely place, with each remaining galaxy marooned in darkness, like an island in a lightless sea. Within those island galaxies, the era of starlight will grind to a halt as well. For a time, new stars will continue to form from the gas and dust left in galactic nurseries. But eventually, around 100 trillion years from now, the fuel for star formation will be spent. No new stars will twinkle into existence. The great age of starbirth, the stelliferous era, as astronomers call it, will come to an end. One by one, the existing stars will burn out. The most long-lived stars, the small red dwarfs, can shine for trillions upon trillions of years, far outlasting our sun's roughly 10 billion year lifespan. Yet even they cannot burn forever. In time, every last star will exhaust its nuclear fuel. Many will die quietly, cooling and fading into black dwarfs, cold cinders where once there was fire. Some heavier stars will die more dramatically, erupting as supernovae and leaving behind only collapsed cores, dense neutron stars or black holes. Either way, the result is the same: darkness. The galaxies, once ablaze with billions of stars, will turn into graveyards of faint, glowing embers and stellar remnants slowly winking out. In the unimaginable far future that follows, even those remnants begin to dwindle. White dwarf stars, those hot, Earth-sized embers left from medium-sized stars like our Sun, will gradually cool over quadrillions of years until they no longer emit any light. They become black dwarfs, essentially invisible, frozen spheres of carbon and oxygen adrift in space. Neutron stars, the collapsed cores of giant stars, may persist as curious, city-sized objects made of densely packed matter, but with no energy source. They too will cool and fade. Planets, if any still survive that long, will be cold, airless rocks, wandering in the dark or clinging to dead stars that provide no warmth. Occasionally, through gravitational dances, some of these extinct systems might merge or collide in the darkness, perhaps momentarily sparking a brief flare of energy. But such events grow exceedingly rare. As time marches on, even gravity's gentle tugs can, over eons, destabilize orbits and send objects drifting away into the void. Meanwhile, the galaxies themselves are slowly unraveling. In the absence of fresh stars and gas, nothing binds a galaxy tightly except gravity. And gravity too can loosen its grip over extreme timescales. One by one, the remaining stellar remnants can be thrown out of their galaxies by gravitational encounters, like lone survivors cast adrift from a dying city. The once grand spiral and elliptical galaxies, now devoid of light, gradually disperse. What was a galaxy becomes a sparse scattering of dark objects spread over immense distances. The architecture of the universe simplifies and empties out. Eventually, almost all matter that is left finds its way into the last refuges of gravity's embrace, the black holes. Much later, in this distant dark epoch, essentially all remaining mass in the universe will be locked up inside black holes. Every stray neutron star or cold dwarf that comes too close to a black hole will be swallowed. Any diffuse gas that still lingers will eventually drift inward and vanish behind an event horizon. Even subatomic particles might not be stable over unfathomable time. If protons decay, as some theories suggest, they would dissolve into radiation, and that energy too would likely end up absorbed by black holes. In this way, black holes come to reign as the last substantial things in existence. They are the final keepers of what once was matter, each one a silent tombstone marking where a star or galaxy once lived. It's a haunting vision. Great black holes, once the dynamic hearts of galaxies, now isolated and alone in the endless night. Like lone sentinels, they drift through a silent cosmos, unseen but still influential, warping the space around them. Each stands as a monument to a bygone era of light. And yet, even these dark titans are not truly eternal. In the 1970s, Stephen Hawking theorized that black holes are not perfectly black. They can slowly evaporate by releasing a trickle of energy known as Hawking radiation. It is an almost imperceptible process, a ghostly whisper of particles and light that the black hole emits as it very gradually loses mass. To a black hole as massive as a star, this loss is absurdly slow. The radiation is so faint that at present it is far colder than the temperature of the universe itself. For all practical purposes, such a black hole would seem unchanging on timescales we normally consider. But given enough time, even a slow leak can empty an ocean. Over trillions upon trillions of years, as each black hole diminishes, its Hawking radiation will intensify slightly. When a black hole becomes extremely small, roughly asteroid mass, it would emit heat and light at a noticeable rate. In its final moments, it may release a last burst of energy, a brief flash illuminating the darkness, before it disappears entirely. This would be the black hole's final breath, so to speak, the last gasp of light in a universe that has gone almost completely dark. The timeline for this decay defies ordinary comprehension. For a black hole of stellar mass, the evaporation might take on the order of 10^67 years, a 1 followed by 67 zeros. For the supermassive black holes once found in galactic cores, the numbers are even more staggering. It has been estimated that by about 10 years into the future, a 1 with 100 zeros, even the largest black holes will have evaporated into faint particles and photons. 100 trillion years is nothing next to this immense span. 100 years, a number called a googol, is so vast that it dwarfs any timescale we have discussed so far. Compared to it, the trillions of years when stars were dying and galaxies fading were merely the opening acts of the finale. But even that near-eternal age of black holes will, in time, come to an end. When the last black hole finally dissolves, the curtain falls on the cosmic story of matter. No planets, no stars, no black holes remain. Nothing solid or structured at all. What is left is a thin, diffuse haze of elementary particles and radiation, spread out across an ever-expanding space. In this final dark era of the universe, no normal matter remains. The mighty drama of galaxies and stars has ended, leaving behind an almost featureless expanse. All the energy that once was concentrated in brilliant suns and whirling galaxies is now diluted into a feeble background glow. The cosmos has reached a state of near-perfect equilibrium. The temperature everywhere approaches absolute zero, the coldest temperature possible, just a hair above nothingness. Even the faint afterglow of the Big Bang, the cosmic microwave background radiation, has by then faded into obscurity. The universe is effectively dark, cold, and silent. It is a solemn ending, a universe drained of light and life, stretching into eternal night. And yet, there is a strange serenity in this vision. After epochs of violence and creativity, after the bright, tumultuous youth of the cosmos, everything finally comes to rest. The once roaring furnace of creation quiets down to embers, then to ashes, then to nothing at all. It is as if the universe has exhaled its final breath and lapsed into a timeless slumber. Like the last note of a cosmic symphony fading into silence, the cosmos finds peace in perfect stillness. No more days or nights, no seasons, no change. Only an endless, unchanging now. Such is the fate our current understanding paints for the universe. Not an explosive finale, but an ever-slowing dimming of the lights, the so-called heat death of the cosmos. No eyes will be open to witness that final darkness. No instruments will record the last black hole's demise. These events are to occur on scales of time and space that utterly dwarf our human experience. Yet from our vantage point in the early universe, we can peer through the power of reason and imagination to that distant future. We can contemplate the death of the cosmos and reflect on what it means for us, here and now. Pondering this ultimate end reminds us of the impermanence that pervades reality. Even the grandest structures in existence, the brilliant stars, the graceful galaxies, are transient. They have their moments of glory, then pass away. It also teaches us to cherish our present era, this brief golden age of starlight in which we live. Right now, the cosmos is filled with galaxies, radiant with billions of suns, and on at least one small planet, alive with consciousness to appreciate it. This is a special time in the life of the universe. In the distant future, there will be no such lights, no life as we know it, no warmth. Realizing this, we might feel both humility and gratitude. Humility at the vast timescales and forces far beyond our control, and gratitude that we get to witness the cosmos in its youthful bloom. Perhaps most wondrous of all is that we, who occupy but a blink of cosmic time, have the ability to envisage these far-off epochs. Through science, we have learned enough about physics and the cosmos to predict how stars will die, how galaxies evolve, and how the universe itself might age. In doing so, we have extended our reach in a way. Our minds can travel trillions of years into the future, long after we ourselves are gone. In contemplating the cosmos, we transcend our brief lifespan and connect with something almost eternal. There is a quiet comfort in that perspective. We see that we are part of a vast, unfolding story, even if our chapter is fleeting. We see that the atoms in our bodies and the light in our skies are participants in a cosmic cycle of birth and death that spans eons. Still, the idea of an absolute end can feel forlorn. It's natural to ask, is that truly the end of everything? Or could there be, hidden in that distant darkness, the potential for a new beginning. History has shown us that in the universe, every end has the seeds of a beginning. Throughout cosmic history, destruction and creation have been intertwined. The end of one phase often triggers the start of another. Consider the stars themselves. When a massive star dies in a supernova, it scatters the elements that become the raw material for new stars, new planets, and maybe new life. In that way, a star's death is not just an end, but also a kind of cosmic sowing for the future. Nature continually recycles and renews. Even black holes, the very entities we've watched presiding over cosmic endings, might play a role in new beginnings. To truly understand how an ending can transform into a beginning, we need to look more closely at these mysterious dark objects. In their shadow, we may find the seeds of new worlds waiting to emerge. The idea that black holes signify only destruction is giving way to a more nuanced understanding. We tend to imagine black holes as nothing but devourers, insatiable monsters lurking in the dark. Indeed, their gravity is so strong that nothing, not even light, escapes once caught. Yet, the more we learn, the more we see that black holes also participate in creation and transformation on a cosmic scale. They stand at the crossroads of endings and beginnings. From the remnants of dead stars to the birth of new stars and even speculative new universes, black holes seem to plant seeds as much as they swallow them. Consider what happens in galaxies. Deep in the heart of a distant dwarf galaxy, astronomers observed something astonishing: a black hole helping to ignite star formation. In this tiny galaxy, about 30 million light-years away, the supermassive black hole at the center was gently blowing a stream of energy and gas outward. Where this outflow struck a dense cloud of gas, it did not destroy the cloud. Instead, it compressed it. Under that pressure, parts of the cloud began to collapse, and new stars were born. To an observer, this small galaxy would now glisten with an unexpected burst of starlight. A once dark region would be aglow with the pinkish hue of ionized gas and the blue shine of hot young stars, a stellar nursery sparked by an unlikely gardener. The usual image of a black hole devouring everything around it was turned on its head. In this case, the black hole's presence was catalyzing growth. Dozens of young stars sparkled to life near an object that would normally be associated with darkness. And it's not an isolated example. In a massive galaxy cluster billions of light-years away, a ferocious eruption from a central black hole has triggered the formation of stars on a huge scale. The black hole's jets blasted out into the surrounding hot gas, carving enormous cavities in the plasma that filled the cluster. As those cavities expanded and then cooled, gas at their edges condensed into clumps, like dew forming after a hot day. We cannot see the ancient jet itself anymore, but the pattern of stars left behind is like a ghostly footprint of its passage. Astronomers observed a stream of about 19 star clusters, arrayed like pearls on a cosmic string, tracing the path the jet had carved. The black hole's eruption, though violent in its moment, left behind this glittering trail, a stellar nursery in its wake. It's a spectacular illustration of nature's paradoxical creativity. From the black hole's destructive power came the materials for creation. Even the mighty blasts of a quasar, it turns out, can have a silver lining, spurring the growth of new stellar communities. Black holes also contribute to creation in more subtle yet profound ways. To see this, we must step back to the life cycle of stars themselves. When a very massive star reaches the end of its life, it may undergo a colossal supernova explosion. The star's core collapses, often forming a black hole, while its outer layers are violently ejected into space. Those ejecta are seeded with newly forged elements, As the star dies, the intense heat and pressure of the supernova create elements that the star never produced during its life. Gold, silver, uranium, and other heavy elements are forged in those fleeting instants of the star's death. The explosion scatters these elements across interstellar space. These atoms blend into vast clouds of gas, the raw material for future generations of stars. Thus, the death of a star, often marked by the birth of a neutron star or black hole at its core, enriches the galaxy with the ingredients for new worlds. The iron in our blood, the calcium in our bones, the carbon in our cells, all those atoms were forged in stellar furnaces and spread through space by supernova winds. Some of those stars left behind neutron stars, and others became black holes as their final relics. In a sense, black holes stand as guardians over the graves of stars that, in dying, gave us the building blocks of life. Without such star death events, there would be no planets rich in minerals, no water, no complex chemistry, none of the essentials that make our world. We owe our very existence to these cosmic cycles of death and rebirth. Even neutron stars, the dense remnants of prior star deaths, can partake in this creative cycle. When two neutron stars spiral together and merge, they unleash an explosion, a kilonova, that forges some of the universe's heaviest elements, like gold and platinum, in tremendous quantities. Such a merger often results in a new black hole born from the combined mass. Thus, the birth of that black hole is accompanied by a cosmic alchemy, the creation of precious elements that will drift through space, to be later incorporated into stars, planets, and perhaps living beings. Even on the grandest scales, black holes may play the role of cosmic seeds. Let us journey in our minds to the dawn of the universe. Only a few 100 million years after the Big Bang, the cosmos is just beginning to twinkle with the light of the first stars and protogalaxies. In those early times, some black holes might already have been taking shape, born from the collapse of the very first massive stars. These embryonic black holes could have served as nuclei around which matter accumulated, helping to shape the first galaxies. Astronomers puzzle over how supermassive black holes, weighing millions to billions of suns, appeared so early in cosmic history. One possibility is that relatively small seed black holes, perhaps the remnants of the very first generation of stars, or even direct collapses of primordial gas clouds, had a head start. In truth, it may be a bit of both. The galaxy and its central black hole likely grew together, each affecting the other's growth. We find hints of this symbiosis in dwarf galaxies, with unexpectedly massive black holes. Even in tiny galaxies, an outsized black hole suggests that black holes were active early, influencing their surroundings from the start. The creative potential of black holes doesn't end with the formation of stars and galaxies. Some of the most far-reaching ideas in modern physics suggest that black holes might be connected to the creation of whole new universes. While highly speculative, these ideas are compelling in their scope. The notion arises from the realization that inside a black hole, the known laws of physics break down. At the singularity, matter is crushed to immense densities, and our equations predict infinities. This is a strong hint that we need new physics to understand what really happens there. A provocative hypothesis is that a black hole's collapse might trigger a bounce on the other side, essentially a big bang in a separate realm of space and time. In this scenario, the interior of a black hole could become the genesis of a new expanding universe, completely cut off from our own. It is as if a seed, falling into darkness, sprouts a new world, hidden from the original. The matter that vanishes into a black hole here might explode as a big bang there. Some cosmologists have even suggested that perhaps our universe was born from such a process, that we are living inside a black hole that formed in another parent universe. If true, every black hole in our cosmos could give rise to a baby universe of its own, like cosmic eggs hatching new realities beyond our reach. One thinker has gone so far as to propose a kind of cosmic natural selection. Universes that create lots of black holes would naturally produce more offspring universes, perhaps biasing the fundamental laws to favor the formation of stars and black holes. In that whimsical view, our own universe might have physical constants finely tuned to maximize the birth of stars and black holes, because those lead to more universes. It's a bold and untestable idea, but it shows how far our perspective has shifted, from seeing black holes as sterile ends to considering them as drivers of an evolutionary process on a cosmic scale. None of this is proven, of course. These ideas remain in the realm of theoretical speculation, awaiting a breakthrough in our understanding of quantum gravity to know if they could be true. Yet, they beautifully illustrate the theme of endings leading to beginnings. A black hole, which appears to be the ultimate dead end where matter and information vanish, could in fact be a bridge to a new creation. The end of a star in our universe, collapsing into a black hole, might be the beginning of an entire new cosmos elsewhere. Even if this particular vision does not hold, it reminds us how intertwined endings and beginnings could be on the grandest scale. What we see emerging from all these insights is a profound cosmic truth. Creation and destruction are woven tightly together. Black holes embody this duality more than anything else in nature. They are born in destruction, in the collapse of stars. Yet through that very process, they contribute to the birth of new stars and planets. They can tear matter apart, yet in doing so, they redistribute the ingredients for new structures. They can lock things away forever, yet they might also be portals to entirely new existences. Once feared as cosmic devourers only, black holes now appear as essential cogs in the engine of the universe, steering its evolution in seen and unseen ways. The next time we look up at the night sky, we might spare a thought for these invisible giants and their hidden influence. The light of distant stars that graces our eyes has been shaped, in part, by black holes stirring the cosmic cauldron, triggering star birth here, stifling it there, and recycling cosmic material endlessly. Even our own existence is tied to stars that lived and died, some of which left black holes behind as cosmic remnants. In the grand scheme, black holes are agents of balance and renewal as much as they are agents of destruction. Through the dark alchemy of black holes, the universe has found a way to continually reinvent itself. Endings fertilize new beginnings. From the darkest places, new light can emerge. This realization transforms our view of black holes from monstrous anomalies lurking in the void to integral, even nurturing parts of the cosmic life cycle. Our exploration of black holes has thus revealed a cosmos where every death feeds new life, and where even the deepest abyss may hide untold wonders. It is a universe where a single object, a black hole, can hold the key to understanding both the end of worlds and the genesis of worlds. Standing at this insight, we find ourselves at a crossroads of reflection. The journey we undertook into the shadow of the black hole has brought us face to face with both the doom and the hope that the cosmos contains. Our voyage through the cosmic abyss now comes to a gentle close. We have wandered in our minds from the fiery birth of stars to the silent death of the universe, from the singularity at a black hole's heart to the far shores of a speculative new cosmos. In the process, the black hole, that enigmatic shadow, has been our guide. We ventured into its darkness, and on the other side, we found not just oblivion, but insight about the life cycle of stars, the fate of galaxies, and the very destiny of the universe. Now, as we step back from the edge of the abyss, we carry with us a new understanding and a profound sense of awe. It is remarkable to think how far our knowledge has come. Not long ago, black holes were considered exotic theoretical curiosities. For decades, they existed only in equations and thought experiments, almost like mythology made of mathematics. Many scientists doubted they could be real. But today, black holes are an established reality of our universe, and we have even seen and heard them in ways our ancestors would never have imagined. In April 2019, human eyes gazed upon the first ever image of a black hole's shadow, a ring of golden light encircling darkness, captured by an Earth-sized network of radio telescopes. This unprecedented picture was of the supermassive black hole in galaxy M87, 55 million light-years away. The world gazed in wonder at this fuzzy ring of light, the shadow of a black hole made visible. Not long after, astronomers achieved a similar feat with the black hole at the center of our own Milky Way, finally peering through dust and haze to see the glowing halo of our galaxy's central dark heart. Even our home galaxy now yielded its closely guarded secret. People around the globe cheered and even wept at the sight of these images, recognizing them as milestones in humanity's quest to comprehend nature. Around the same time, another groundbreaking feat unfolded. Scientists detected faint ripples in spacetime, gravitational waves, emanating from the collision of black holes eons ago. These whisper-like vibrations were recorded by exquisitely sensitive instruments, a triumph coming 100 years after Einstein's prediction of such waves. At last, we could literally hear the final moments of two black holes merging into one. When this faint chirp was first picked up in 2015, confirming a black hole collision 1.3 billion years away, scientists around the globe rejoiced. It was as though the universe had spoken a new word to us, and we had heard it, a gentle cosmic melody carrying profound meaning. Each of these achievements stands as a testament to human curiosity and ingenuity. They have drawn black holes out of the shadows and into the light of empirical science. Moments like these remind us of the power of the human spirit in exploration. We imagined what seemed unimaginable, and through decades of effort, we made it visible and audible. The story of black holes is also a story of our species' determination to understand, a triumph of imagination married to experiment. Yet, for every mystery we have solved, new questions have emerged. Black holes remain one of the greatest frontiers of modern physics. Deep inside them, at the singularity where density becomes infinite, our current understanding of natural laws breaks down. What actually happens in that hidden crush of matter? Does space and time come to an end, or transform into something else? To answer such questions, we need a unification of quantum mechanics and general relativity, a theory of quantum gravity that remains elusive. In grappling with black holes, we are pushing the boundaries of knowledge on the smallest and largest scales. These dark entities force us to confront the very nature of reality. and through them, we may one day uncover a more complete description of how the universe works. Black holes also pose profound philosophical questions. Consider the so-called information paradox. According to standard theory, anything that falls into a black hole is lost forever from our universe. Not only physically gone, but its information, the unique details of its state, seemingly erased. This idea deeply troubles physicists because it clashes with principles of quantum physics that say information cannot be destroyed. Is the universe truly forgetful, or do black holes somehow preserve or release the information they absorb? No one knows for sure. Some theories suggest that information might be encoded in subtle quantum imprints on the event horizon and slowly released back via Hawking radiation over eons. If true, a black hole would function less like a tomb and more like a vault that eventually returns what was put inside, though in a highly scrambled form. The resolution of this puzzle is still pending, but it teaches us a humbling lesson. There is a layer of reality we have yet to penetrate. In the end, the information paradox is not just about the fate of some particles falling into a hole. It speaks to a basic question about whether the universe fundamentally makes sense or not. As we continue to study black holes, we are, in a way, interrogating the universe about its most closely held secrets. Throughout our journey, one theme has surfaced again and again: interconnectedness. Black holes are linked to everything else in the cosmos. They are born from stars and influence the formation of new stars. They anchor galaxies and stir the cosmic web. They challenge physics and inspire new mathematics. And through our study of them, they connect us to the far reaches of space and time. In uncovering the story of black holes, we have been participating in a grand human endeavor to weave together the narrative of existence itself from the threads of observation and reason. It's a narrative that tells us we are not isolated observers standing apart from the universe, but rather participants in its story. Through our very existence, the universe is able to reflect on itself. We are made of its very substance, and now we turn back to understand the whole. After all, the iron in our blood was forged in a star, and may be tossed out by a supernova that left a black hole. The water in our bodies was enriched by cosmic alchemy. We truly are, as the poet said, made of star stuff, and black holes have played a role in shaping that inheritance. Recognizing this kinship can fill one with a sense of belonging, a calm awareness that we are at home in the universe, no matter how vast and dark it may sometimes seem. And what a vast and dark cosmos it is. Standing under a clear night sky, we can gaze up and see the band of the Milky Way, unaware that at its core, a monstrous black hole resides in quiet vigil. We can see stars sprinkled across space, not realizing that many will one day collapse and perhaps become black holes themselves, continuing the cycle. Our journey into the shadow of black holes has illuminated the night for us. The sky we return to now is the same, but our perception of it has changed. Where we once might have seen emptiness in the dark, we now sense fullness, a tapestry woven of countless stories of creation and destruction. Each point of light overhead carries within it the fate of maybe becoming a black hole, and each darkness carries the promise of light emerging again. As this exploration concludes, we find ourselves at a threshold rather than a terminus. Every answer we've found about black holes begets new questions. In the near future, new observatories and experiments, more powerful telescopes, more sensitive gravitational wave detectors, will peer deeper into these mysteries. They may answer some questions, and undoubtedly will raise others. In that sense, every ending truly is a new beginning. The end of this documentary is the beginning of your own continued contemplation. The end of a star becomes the beginning of new worlds. The end of our old fear becomes the beginning of wonder. In the grand scheme, the universe itself may cycle through infinities of time, an end that becomes a beginning in ways we can barely fathom. And even if it does not, even if there is a final quiet end, we have seen that within that end lies the subtle seed of something new in another form. Now we pause and simply breathe in the cosmic perspective we have gained. Think of the immense scales of time and space we have traversed, and then bring your mind back to the present moment. Here we are, tiny beings on a small planet orbiting a middle-aged star, reflecting on phenomena that span billions of light years and trillions of years. That we can do this, that we can ponder our place amidst such immensity, is a quiet miracle of consciousness. How fortunate we are to exist in this era of cosmic light, when galaxies still shine and the universe's story is accessible to us. 1 trillion years hence, the skies will be dark and mute, but right now we can witness the cosmos in its vibrant glory and learn from it. It is a source of comfort and inspiration. The darkness of a black hole or the night between the stars is not something to fear. It is a canvas for our curiosity. We have learned that even in darkness, the universe is teeming with process and purpose, forging elements, birthing stars, perhaps even nurturing nascent universes. The unknown isn't a void to be dreaded, but a mystery to gently embrace, knowing it harbours the potential for insight and awe. As you listen to these final words, perhaps you feel a sense of calm wonder. We set out to explore terrifying behemoths, and we discovered a profound truth about balance and renewal. Black holes, once symbols of destruction, have shown us the unity of creation and collapse. Likewise, our own quest has come full circle, revealing that knowledge and mystery exist in harmony. We do not have all the answers, and likely never will, but that is okay. The cosmos retains its secrets, and therein lies its eternal allure. In the face of such grandeur, many of our everyday worries fall away. We realize how small our moments are compared to cosmic eons, and that understanding can bring a gentle sense of peace. Knowing we are part of something vast and meaningful can make us more serene about the trials of life, for we see the bigger picture. So, under the eternal sky, we conclude our journey. The stars above shine as they always have, but to us, they now speak of more than light. They hint at the cycles of time, the work of gravity, and the unseen influence of black holes, silently shaping the cosmos. Take a moment to feel the stillness of the night, the quiet of the universe as it is. In that silence, you might sense the echo of all we have spoken of, the faint dance of orbiting stars, the distant merger of black holes, sending ripples through space-time, the birth of light from darkness. It is a peaceful symphony, one that has played for eons and will continue long after we are gone. Our journey's end is, in truth, a new beginning. With our minds opened and our hearts humbled, we step back from the cosmic abyss and return to our daily lives. But we do so changed, carrying the tranquility of understanding. In the grand dark of the universe, we have found not despair, but a deep kinship with everything that is. The next time you look up at the night sky, you may feel a gentle smile form, knowing that beyond what you can see, the story of creation and transformation continues, and that you are part of this magnificent story. In that connection lies a profound peace. In the shadow of black holes, we discovered the light of comprehension. As we bid farewell to this journey, we are left with a quiet wonder that will never fade. The cosmos is vast and mysterious, but it is also our home. And as we float here on our small world, bathed in starlight, we can rest in the understanding that the darkness is not empty. It is full of promise. Every ending blends into a beginning. Every question leads to another. And the awe we feel is the bridge between not knowing and knowing, a spark that will guide us onward. As we close our eyes tonight under the quiet sky, we remain, always, in the gentle embrace of the cosmos, forever part of its endless story.